Hi, I'm Lawrence Krauss, and welcome to the Origins Podcast. Scott Aaronson is quite simply one of the most remarkable mathematical intellects I've had the pleasure to interact with since, say, Edward Witten, who is a remarkable physicist and string theorist, and has really is the only physicist I know who also won the Field Medal for mathematics. Scott reminds me of Ed in the depth and breadth of his thinking, and it's kind of appropriate that I actually first met Scott in Washington a number of years ago when we were both getting awards, but he was getting the Waterman Prize, which is basically the highest award of the National Science Foundation for young researchers under 40, and the first person who'd ever won that prize was indeed Ed Witten. It's a pleasure to have known that Scott won that award, and since that time, when we briefly met, I've come to watch and learn as Scott, as a computer scientist, applies his mathematical expertise to a broad variety of areas, thinking in particular about quantum computing, an area which he's become a leader in pushing forward the theoretical ideas necessary to think about what quantum computing can and can't do and how it could do those things. He also writes a fantastic blog explaining quantum computing people. And then, of course, recently, he's moved to the idea of AI safety. He spent some time at OpenAI and been thinking deeply about how one can implement the kind of safety measures that many people worry about when they think about unrestrained general AI in our society. I happen to think many of those societal concerns are overblown, but nevertheless, fortune favors the prepared mind, and his mind is wonderful, and the preparations he's been doing are incredible. So we were able in this episode to talk about everything from computer science to AI safety, focusing on this rather esoteric idea of computational complexity. And so we worked through some rather sophisticated ideas in computation to talk about the basics, many aspects of quantum computing, which complement nicely my earlier podcast with John Preskill, who's a physicist who's come into that field. And it's interesting to see how a computer scientist thinks about those same issues. And then we move to the thorny question of AI safety and some of the remarkable ideas that Scott has with regard to that. It was a remarkable conversation. He's as I say, an extremely deep and thoughtful intellect, and it was a pleasure to finally be able to spend time with him again. I thank him for being on it. I think you'll find it amazing. I hope you enjoy the podcast. If you want to watch the podcast without commercial interruptions, I hope you'll subscribe to our Critical Mass Substack site. And all of the paid subscriptions for that go to help support the Origins Project Foundation, which produces the podcast, among many of the other public science programs that we do. And if you can't do that, you can certainly watch it later on YouTube, or of course listen to the podcast on any podcast site. Regardless of how you do so, I hope you are as inspired and provoked by the thoughts of Scott Aaronson and quantum computing, and of course the issue of AI safety, which is going to be becoming more and more important as AI systems become more sophisticated. So without further ado, Scott Aaronson. Well, Scott, thank you so much for making the time to be here. It's great to see you again. It's been a while, actually.
Yes. Thanks for having me.
I've been looking forward to this, and as I'll explain, dreading it for the same reason, because I admire you so much. We first met, I think, at least 12 or 13 years ago, maybe 14 years ago now, 13, I guess. I think that was the first time we met when we were both getting awards from the National Science Foundation, and we shared a limo in Washington, in the State
Yes.
Department. And I confess, so I was getting some public service award, and was that where you received the Award?
It was.
Yeah,
Yeah.
I confess, maybe because I was so into myself that time, that I forgot it was a Waterman Award till much later. And it's just as well. Anyway, it was an amazing night. It was a lovely evening, and it was lovely to meet you. Were, I think, newly married then, or
I
maybe,
was, yes.
and
Yes, my
it was
kids were
lovely.
not yet born. Yes.
Yeah, yes, your kids weren't born, and it was lovely to see
Mhm,
you and your wife. Yeah, a young
mhm.
couple. So excited about this award. I knew it was an award for young people, but the Waterman Award is the highest prize that the National Foundation Science Foundation gives to a scientist under 40. And I normalize it, let me say, because I remember when it first was created. I'm old enough, and I remember when they asked for nominations. And it wasn't surprising to me that I think the first recipient was Ed Witten, um, who is, I think, by almost anyone's standards, the smartest person in the world. Um, and I thought, okay, well, that's a nice bar. And I have to say, that having thought about, I've known things, I've known of your work and read some things by you, but deciding to go into understanding you, I suddenly realized that I had the same feeling that I have when I was talking to Ed, who's an old friend of mine and a nice guy as well. But the kind of the sense of the depth and breadth of your intellect is remarkable to me. I'm saying that outright. I'm intimidated in some sense by it. It's astounding. I want to hopefully do it justice. I think the problems you're looking at are interesting, and the way and your attitude is refreshing. You add a difference in the sense that you also like to write about your problem, your thoughts, which I don't think Ed does. But I kind of feel, as a
Yeah.
preview of what we're going to talk about, I kind of feel that
Well,
that when you talk about computationally hard problems,
mhm.
uh, for me, you're a computationally hard problem. And this, I may require not computing polynomially time, but exponential time to fully grasp um, um, uh, your intellect. And in that sense, and I'm going to say things that people will understand right now, but we'll get to it. In that sense, I'm hoping that P is equal to NP, because I'm hoping that I can somehow understand um, how to get to where you are.
Well,
And
you're extremely kind. I mean, I have gotten to know Ed a little bit over the last 5 years through the It from Qubit collaboration and things like that. I will certainly not be able to simulate him in any way, shape, or form. And
well,
I
it's
feel like the questions that I work on seem ridiculously elementary in many ways. Compared to what my friends in string theory do. But I like being in a field where that's relatively young and where the questions are very easy to state.
Yeah, well, something that, but as you just alluded,
Yeah.
questions that are easy to state are not necessarily easy to answer. In fact,
No,
sometimes
not at
they're the
all.
hardest ones to answer.
Mm.
My new book's about known unknowns, and in some sense,
Mhm.
as I say at the beginning of the book, and it really hit me, is that the problems at the forefront of science that we don't understand are precisely the problems that almost everyone has asked themselves at some point
Yeah.
or another. So it's kind of interesting to see that.
Mhm.
But on the other hand, I can ask questions without making sure I understand what the questions are. In fact, I was thinking about that because we'll get to ChatGPT. I'm hoping that we may have a very fascinating discussion, even if I'm kind of like ChatGPT, where I don't really understand exactly what the questions I'm asking are, or what you're saying is, but I know how to get there. So anyway, let's see where we'll go. I find it
Sure.
fascinating, and I should say that you know I I wanted to talk to you as initially also for a variety of reasons. One, because I wanted to talk to you, but also as a compliment. As you may know, I did a long podcast with my old friend John Preskill,
Mhm.
who goes back with me back to when we were at Harvard together, and
Mm.
before he started working in quantum
Mhm.
computing. I like to kind of
Mhm.
think that the issues we worked on black holes and information are really what may have spurred him into thinking about quantum computing. I watched that transition happen as we were working on
Yes.
papers.
Yeah, no, John has been instrumental in my career. I mean, one of the most important summers, that I ever spent was at Caltech in 2001, going to his group meetings and, just feeling invigorated after every one to,
He's a remarkable teacher in many ways.
understand what quantum mechanics says about computation. Yeah,
Yeah, no, but he comes at it from a different point of view. He's
he
not by
does.
training a computer
That's
scientist,
right.
and you are. And I thought, quantum computing, which we talked a lot about with him, I thought the more different directions you can come at it from, the more useful it might be from the public. But but I wasn't, so that's where I wanted to start. And then when you sent me things to read, when you
Mm.
finally sent me things to read, when I asked you, maybe some sources, it of course went way beyond quantum computing, and as we'll talk about, your interest in the last year at least has been in AI safety, which is something that's on everyone's mind. But in the interim, what I began to learn about that your real interest, where your heart is computational complexity. I think that's a fair statement. The
Yeah,
mathematical question of computational complexity. So I want to talk about how we got there before we start
sure.
talking. We'll talk about quantum computing, computational complexity, and AI safety. Hopefully, we'll get through it in the next day or two. But as you may know, if you've watched any of these, and maybe you haven't, I like to. It's an origins podcast, and I like to start by learning about the people I'm fascinated by, about their origins and how they got to where they now are. Now, the first thing I learned when I read a little bit about you is that your father was a science writer who then became a public relations executive.
Yes.
So was his training in science, or was his training
He
in
was
writing?
both of my parents were English majors.
English majors. Okay, perfect.
Yes. Mhm.
Well, that does explain some things. Well, that's of interesting. But English
Mhm.
majors clearly, well, in your father's side, and I want to ask about your mother a little bit because I don't know anything about
Yeah.
her. But in your father's
Mm.
side, I think it's great when English majors become science writers, because ideally, if an
Mhm.
English major can understand it, then anyone can understand it.
Yeah.
And so it's better they don't get lost in jargon. But what caused him to be a science writer?
Well, he studied at Penn State, and he actually studied with a somewhat well-known science fiction writer named Phil Klass,
Okay.
and he was, extremely interested in, well, in science and in science fiction, and he he found jobs, writing articles about, the Big Bang, about cosmology. He interviewed Steven Weinberg. Actually, when I first met Steven Weinberg 7 years ago, when I was considering moving to UT Austin, he confused me with my father, who he had still remembered from
Oh, really?
being interviewed by him in the 70s.
Oh,
But
fascinating.
he wrote for science magazines. He also wrote for Playboy and Penthouse, which he said
Which I maintain had great
paid better than the
articles.
science magazines. He
I
said,
used
yeah,
to
yeah,
tell my
right,
mother
right,
that I
right, right.
read
No, I mean,
Playboy
so
for the articles, and I
he
did.
had these Playboys in his office, right? But he could legitimately say, like, I have an article in here about why is there more matter than antimatter, in the
And they had great
and
interviews. Claudia Dreyfus is an old friend of mine. She
yeah.
was a science writer, and she used to do interviews for them. She interviewed me once, and it ended up being
Hmm.
for Scientific American. But
Hmm.
yeah, no,
Yeah.
it was a great source of. It's a kind of
Yeah, so
interesting.
that was what he did in the 70s, and then he was hired by Bell Labs to be a science writer there. And
Oh,
actually, when Penzias and Wilson, won the Nobel for the
yeah.
cosmic microwave background, he was involved in, the publicity efforts around that, right?
Oh,
And so he got to know Arno Penzias well, and
a
uh,
mixed
but
blessing. Okay.
and then, when Congress was, debating, breaking up AT&T, he was responsible for, writing speeches about, why is this going to destroy Bell Labs, which of course it did destroy Bell Labs. On the other hand, we all got, cheap phone service, so
Yeah.
that was the trade-off.
Yeah, it did destroy Bell Labs, and nothing like a
Yes.
monopoly if you want to spend time on research. Doesn't
Yeah,
want to
and
spend
then he
money, not this time.
and then he moved to the corporate side, and
Became
by the
public
time I
relations
was
for
growing
Bell,
up,
for AT&T.
yeah, no, he was at AT&T, and then at Lucent after they spun off
Yeah. Okay.
Lucent, and then at Avaya. So yeah,
Now,
so
did he
that's
write? Did he ever write any science fiction, by the way?
I believe he did.
But you never saw it? No,
No, years ago, I probably read one of his short stories, but no, he was also, constantly, giving me feedback on my writing, usually just telling me to cut, cut, cut,
well,
just
it's
yeah,
interesting.
omit needless words,
Yeah,
like
yeah. Well,
Drunk and White say.
I
It didn't completely take that advice.
well, that's okay. I like.
Yeah.
For me, I often, especially when I'm trying to understand something, more is sometimes better. Um,
Mm,
but it explained a lot to me when I learned a little bit about your father, because
mm.
you have been involved with, and in spite of the fact that for many people blogging is the death of their science. I know at least one physicist who I'd say that for, but
Really?
yeah, yeah, I think so. I'm not going to mention names, but
I feel like blogs are already something that like you look back on with nostalgia. Like, gosh, people really express themselves, in depth, and back in that lost golden age of blogging, right?
well,
Now it's
it's
all
great. I
just
mean, but
tweets
some
and
of the
yeah,
your blogs have been
yeah,
very useful for a lot of people, and that's great. And
mm,
but now I understand why you're motivated, at least the example of why you're motivated to write, because your intellectual interest is in an area that is in some sense as far divorced from public explication as you might imagine,
mm,
especially since it involves mathematical complexity, two words which generally are an anathema to the public. And so yeah, so now I understand where you got that interest from. And by the way, I know you've got a great idea for a science fiction story. You've told it enough that I'm expecting someone else
mm,
to write it.
mm.
If you don't, but maybe we'll talk about your science fiction story
All
we're
right.
done, because it's a great idea. I agree,
Mm.
but you have to know enough to know
Mhm.
what the hook is for science fiction. What about your mother? Your mother was an English major.
Yeah, my mom was a remedial reading teacher, and she actually taught for decades in inner city Philadelphia. Um, and she worked at Catholic schools mostly.
Uh-huh.
But the but she was an employee of the city, right? And the Supreme Court, kept changing its mind about whether she was allowed to be in the building or whether she had to be in a trailer outside the building. It was a big separation of church and
Yeah, it's
state
in state.
case.
Yeah, yeah, yeah,
And
yeah.
but she was these although kids went to Catholic school, if they had reading difficulties, they were entitled to
Sure.
specialist to help them. And so she was an expert in that. And I think that she could have probably been done research in that area, and done much more in it. But she really sacrificed a lot for for me and my brother. I mean, she wanted a job where she could be there for us. So
Well, that's lovely.
yeah,
Now,
yeah.
which one of them, or maybe both, was, because he was a science writer, is that what sparked your interest in science in the first place?
Oh gosh, I mean, it's kind of like how
How
you
could you
hear
not be
that there's
interested?
a
I know,
you I mean, you hear that there's a maximum speed that anything can go at, right?
but a
And
lot of people don't hear that.
it's
Where you must have heard it.
186,000 miles per second, right? Like how can you not want to understand?
Yeah, but a lot of people don't
What
even
would
know that
happen if I
fact. So
tried to go faster, right?
yeah, sure, but where did you first hear that? A lot of people don't have never heard
Well,
that.
my dad told me, a bunch of these things when I was 4 or 5. Um, let me think. I had science books that I read.
So
I think, at some point, when I was 10 or 11, I started devouring Isaac Asimov. Uh,
me too. I was a
yeah,
little older, probably 13, Isaac Asimov, and I read
yeah. And
George
then
Gamow as well, but
yeah,
a
okay, yeah,
little older.
and then after that came Richard Dawkins, Carl Sagan, Bertrand Russell, and then I just started devouring biographies of scientists. So biographies of of Einstein and Turing and Ramanujan,
Yeah, yeah.
and just learning about the whole world, so the whole almost
Well,
vanished
let's go
thing.
back. I mean,
Yeah,
that's the
yeah,
next thing I
yeah.
was going to ask. So you were you uh, it's you got part of your interest in sciences from reading, and that's certainly what sparked.
Mm,
That's what got my interest going.
mm.
But was there? I assume because they're both English majors, reading was a big deal for you. You read a tremendous amount when you were younger. Your parents encouraged that.
I read a pretty good amount. I mean, I was also playing Nintendo a
Yeah,
lot,
yeah, yeah.
right? Once I had that, right? And I think that for a while my main ambition in life was to create my own Nintendo games, right?
Well,
Because these were whole universes, and yet, unlike our universe, these were universes that apparently someone completely understood because they had created them.
Well, that's
Yeah.
not too different, it seems to me, from where you ended up. But we'll
Mm,
see. But
mm,
we were joking that your kids like to play with, on their iPads, and I said
mhm,
if you were their age now, that's what you'd be doing, I think. But you got exposed to science in some sense, primarily through your dad, and through the access to books and books by scientists and about scientists,
mhm,
which of course
mhm.
certainly one of the reasons I write is to return the favor. Um, but you also had another experience that I assume was formative. Your father you went to Hong Kong for a year, and
Yes.
that took you to a school that allowed you to do mathematics way beyond what would have been
Yeah,
possible
well,
in
it
an
was
American
it,
school.
it was it was it was a little complicated. So, I for 9 years, all through elementary, I went to a Hebrew day school. And it was not because my parents were particularly religious. It was mostly that the Hebrew day school, alone among all of the schools, said, okay, he can take a math book and he can proceed at his own rate, right?
Ah,
And um, and then I went
let me
to
step back. Let me
yeah,
just step back.
yeah,
No. I'm
yeah.
sorry, but I'm interrupting you here for a reason.
No, it's
Often I
fine. It's
don't.
fine.
But
It's
no, I
fine.
interrupt too much. I know everyone tells me, but you could take a back math book with you. You were precocious, beyond precocious as a mathematical person. Where did the interest in math come from, as opposed to
Oh,
science?
well, that's as early as I can remember, really.
Okay, so
Mhm.
you just were
Yeah, I mean,
fascinated with.
yeah, I know. I mean, I think, when I was 3 or 4, I was interested in just what are the biggest numbers that I
Did
could
you
name.
talk to any about that, or did you ask
Yeah,
your?
I mean, to my parents, and then at school, I had a teacher who was really formative for me, named
So encouraging teachers for
Mrs.
young people,
Mrs.
another
Lacka.
formative thing. Okay.
Yes,
And
yes,
then
and
encouraged you to keep and so in
yes.
Jewish day school or whatever,
Mhm,
you
mhm.
could follow math, and they let you do that, which
They let me, at least be somewhat accelerated. And then, in seventh grade, I went to public school, and was allowed to be to do the honors algebra then. And then I and then after that is when we all moved to Hong Kong for a year, because my dad became the director of AT&T's Asia Pacific Public Relations
Mhm.
division, and so they paid for us to go to a fancy private school for for expats, and for Chinese people who could
Yeah.
afford it. It's called, Hong Kong International School. But there I was placed in eighth grade. But it turned out that it would not work for me to go over to the high school to take math. It just didn't work logistically. There was also bullying. There was a lot of things I didn't like about it. And so then ultimately we convinced them to just let me skip to ninth grade entirely. And then and then also skip more in math. Math in some sense was sort of excuse. At this point, like as soon as I understood that like it was possible to do such a thing,
Hmm.
then I just sort of wanted to get out of the school environment as quickly as I could, and I still don't know whether I was right, think things ended up better or worse. But when I came back to the U.S. The year after, then I was like, well, I was in ninth grade, but it was really sort of like 10th grade. So really I should be in 11th grade. and uh and so then I did that, and then I finished the AP calculus that year, and then the school had said that I would be able after that to just take, Stanford had this online learning course, and I could do multivariable calculus or differential equations, but then it turned out that I couldn't do that, not even if my parents paid for it, right? I wasn't allowed to even just sit in a room to do that. And so I said, again, I used that as an excuse. And I said, there was a program in upstate New York called the Clarkson School, where you live at Clarkson University, which is,
Yeah.
way up in
Yeah.
Potsdam, and you
Yeah.
just take college courses, and you do that as your senior year of high school. So I said, why don't I go there? And I had many reasons for wanting to get out of high school, but my parents, after some convincing, were kind enough to let me do this. And we had the car all packed up, ready to go there. And like as the car was all packed up, then we got a phone call from a teacher at the high school who, like one who had really supported me. And he said, I have great news. I finally arranged that he can take multivariable calculus. But by then it
Right.
was too late. And so then I was 15 when I started college, and I after a year at Clarkson, sometimes your original high school is nice enough to give you a diploma, but mine would not, because I was missing phys ed. So they said I
Oh.
had to spend the summer doing push-ups, basically. And this was a problem because I had gotten, I had applied to other colleges, as a freshman, and Cornell was nice enough to accept me out of all the places I applied to. So I was going to Cornell, but I needed a high school degree and to enroll. And so then eventually the plan was for me to just get a New York State GED. And there
Uh-huh.
was a rule that you had to be 17 to get it, but my mom spent some hours on the phone with them and convinced them to give me a GED. So
And you were what, 16? You were 15.
I was 15 at the time. Yeah. And then 16 when I started at
So
Cornell.
when you
Yeah.
started. Now,
Yeah.
your grades, it's true that not only did you not enjoy your high school because of their restricting
Mm.
you from doing what you wanted, but your grades weren't that good there either, were they?
Yeah, I mean, I had a lot of conflict with a chemistry teacher, for example, who gave me a C. And I just remember, the one thing I clearly remember from that class is that, like, when you had a calculation to do, even if you had the right answer, it would be marked wrong if you didn't write 1 mole divided by 1 mole
Oh,
and then
yeah.
cross both of them out.
Well, I'm going to sympathize a little with your chemistry teacher. Namely, when it comes to physics, often and chemistry is just really a part of physics. But understanding dimensional quantities and is very useful for understanding how to get the right answer and even what the right equations
No
are. So,
doubt, no
so I'll
doubt,
give
no
him. I'll
doubt.
give him.
But
But on the other hand, chemistry teachers next to math teachers are often the worst in the world. So,
Mhm.
so
No, but also, I was, it became clear that I was not good at chemistry experiments, right?
yeah. Well,
And
sure.
but high school labs are such a weird thing because you are graded on whether you get the answer you're supposed to get, and the incentive is overwhelming to just fudge things to get that answer.
Yeah.
It's
Yeah.
like
Yeah.
teaching the opposite of what you want to teach people if
Yeah, I
they're
agree.
supposed to
It's
to,
the
to become
process, not the
scientists.
process is
Yeah,
what's important.
yeah,
No, and
yeah,
that's a lot. We
yeah.
won't, maybe we'll get into education later on,
Anyway,
but
yeah, yeah, sure.
process and asking questions, not the answers,
Mm.
especially in a world where we have smartphones and soon
Mm,
other and chat GPT.
mm.
Um, uh, but okay, you enter Cornell, but now, by the way, at the same time, one thing we skipped, and this will become relevant later on. So you're prodigiously talented in mathematics, clearly. Um, but you also were, started at the same time as you learned calculus around age 11, you also started to do computer programming. It felt
Yes.
like you were already way behind the curve. Was that because you
Yeah.
had friends who'd been doing it from the time they were five, or just because you
Well,
ran?
I met when I was 12. At my junior high school, I met another kid named Alex who had been programming for much longer than me. Could create amazing things in Visual Basic, and it was clear that I was never going to be as good as he was. Now he became my best friend. He still is. He's now a very well-known computer security researcher,
Oh,
Alex
that's great.
Alderman. He's often in the news for, especially in the last few years, for studying the security problems with electronic voting machines.
Oh,
But
wow. Oh,
but
that's a great
even
story.
when we were 12 years old, he was extremely interested in hacking the school computers, and
Well,
sort of showing how ridiculously poor the security was, and he had a sense of sort of what was actually going on in the machines, right? Not just what could in principle be going on, but but what was. I think Alex was part of how I learned that I am not cut out to be a software engineer.
well, but that was probably very useful for you because you could, I
Yeah.
mean, I know a lot of smart kids who just get in that morass of
Mm.
programming and building apps. And so, of course, some of them become rich. That's a different
Yeah.
story. But
Yeah.
when they actually have the aptitude to do other things, and it's very seductive. And of course, the money is
Right.
very seductive if you're a young person.
Right. Well, there. I mean, there is this kind of running joke that we see someone who left a PhD program and start a Google
Yeah,
or an Amazon and
yeah,
get $20 billion, and we say to ourselves like, man, it's so sad. They really could have been something.
yeah, yeah,
Like,
that's right. I think of Nathan Myhrvold, for example,
I mean,
who
that's.
wasn't able to get a
I
job in
mean,
physics, but he did okay.
right.
Yeah.
Right. That's one perspective you can take. But I did face this sort of decision point when I was a teenager. Like, this was the time when all of these internet companies were being started. I knew that there was this cool research project at Stanford, or something called PageRank, that
Hmm.
these guys Brin and Page were doing, right.
Yeah.
Because I had also been thinking about how do you optimize the web? How do you think about the web as a directed graph? Those were that was actually the subject of my first paper, which I
Wow.
did when I was at Clarkson when I was 15.
You could have been rich.
Those were all things of great interest to me. But do I try to go to Silicon Valley, start a company, or do I go into research? And I feel like I think the way I put it recently was that, like, in the end, I was too selfish to try to get rich. Like, like like if I did make a even if I succeeded at making a ton of money, which is not at all certain, it would just face me with the burden of figuring out what to do with it, and
Yeah,
how
yeah.
could I have an impact on the world, and
It
then
wasn't into
that would.
making
Yeah,
a lot of
yeah.
money was not intellectually interesting. I know that feeling when I was
Well,
younger. I certainly had it.
it might well have been. I mean,
You never
but
know.
yeah, that was that. In any case, that's a different branch of the wave function.
Yeah, it
So
is a different way from
yeah.
it's a difference. It's a different set of skills. I created a program in physics entrepreneurship once when I was chair of a department, and I
Hmm.
learned how different having a successful company is than having good ideas. It's a very
Mhm.
different thing, and
Right.
so different set of
I mean,
skills.
now I've, a little bit. I'm coming full circle because now I'm on leave. I am working at OpenAI. I'm
Yeah.
out in San Francisco a lot, and it is, it's so bizarre to go there, right? Because I still think of myself mentally as like this little kid, this little teenager, right? At OpenAI, I think I am literally like the oldest person there. Okay. Just about everyone is, in their 20s, and, and I'm like, well, the way we thought about machine learning back in the 20th century, which none of you young uns remember,
Okay. Now, well, we're going to get to where you are now, but we'll get there. We're
yeah.
almost done. I am intrigued though. When you entered Cornell, you decided to do a BSc in computing, and I mean, you think like a mathematician. When I read you, it reminds me of reading mathematics. So I did a degree in mathematics and one in physics, and I quickly
Hmm.
became clear to me, even though I was good in mathematics, that I was a physicist and not a mathematician. And I got the same sense of impenetrability about some of your thoughts that I do have in mathematics. And so, why did you do computing rather than mathematics?
Yeah. Well, okay. So there's a sort of silly reason. I took enough math to be a math major at Cornell,
Uh-huh.
but in order to be one, I'd have to be in the College of Arts and Sciences, and then I would have to take 2 years of a foreign language.
Oh, I see.
And at the time, that just seemed like, a big waste to me.
Yeah,
Just like, when I had been at Jewish day school, learning Hebrew, it
yeah,
seemed like the biggest waste to me. Now I'm
yeah.
married to an Israeli, and I wish that I had paid more attention.
Oh, okay, interesting. I dropped out of Hebrew school 3 times in a row
But
myself.
I never had any great facility with foreign languages. I also tried to learn Mandarin the year that I was in Hong Kong, and that was also not a great success.
Uh,
But
That's fascinating to me.
I was in the College of Engineering, and I was doing computer science there, and I did, take a little bit of physics. And I realized that my mind just does not sync with partial differential equations. Like,
Interesting.
okay, I like, okay, yeah, at some conceptual level,
Yeah.
I understand, but I just I wasn't good at them. And also, the moments in the physics class when I got the most engaged was, when there was a mathematical point, right?
Yeah,
Like,
no,
is
that's
is
fascinating.
this set
It
countable or uncountable? Yeah, yeah.
it was
And
fascinating for me. It was a revelation
yeah.
for me. I did a degree in math and one in physics, and I and
Mm,
and I was in, therefore in the honors math, and I was with
mm,
some really good mathematicians, and it shocked me because I figured if you're a really good mathematician, that physics would be trivial, and
mm,
it shocked me that these guys who were light years beyond me in math, I felt I couldn't, even introductory physics was difficult, and it was interesting to me to see that. It was actually made me feel
mm.
better, of course, in
Yeah.
some sense, because physics was, the difference for me was that I could, when I was doing physics problems versus math problems. I want to ask you this: with the physics problems, I could see way down where we were going and
Mm,
where the future was. Math
mm,
problems, I could do them, but somehow
mm,
I could only see just one step beyond where I
mm.
was at best,
I
and
see. I see. Yeah, no, I mean, so I've spent my whole career in quantum computing, interacting with physicists who are the
yeah.
majority of the field,
Yeah.
and very often feeling like an imposter because, okay, at some point I learn what Hamiltonians are. I learn how bosons and fermions work, right? But these are all just things that I pick up on the streets,
Well,
as,
that's all
as,
right. I
as
mean,
it
it's
were.
picking up
I think my retirement project will be to really seriously study quantum field theory and also general relativity, right?
great.
And
Okay. Well, you
but on the other hand, what I realized, like, pretty early on, after I had gotten into quantum computing, was that there could be particle physicists, right, who are like asking me to explain the Bell inequality to
yeah,
them. Right?
sure. Yeah.
Like the things that that were just the most basic to me were often things that the physicists didn't understand and wanted to understand.
Yeah, because they didn't really
And
need to know, and in some sense, Bell. I mean, you
so
work with quantum mechanics, you
yeah,
don't need to
that's
know
right.
Bell's.
That's right. That's right. And so I actually, had a whole like little career just giving colloquia in physics departments, explaining the
Yeah,
basics of quantum information and
yeah,
quantum computing, which, I didn't have to explain quantum field theory because
yeah,
they already know that,
yeah,
right?
yeah, yeah, yeah. No, it's
Yeah.
now. I will say one other. I'll interject one other thing. I don't want to interject myself too much, but it's
Yeah,
when
yeah,
you say
sure.
you didn't do this because of You didn't want to take foreign languages. It's intriguing to me because when I was reading all your stuff, it occurred to me how wrong I was about something. The first professorship I had at Yale was at Yale, and I
Mm,
think I got put on as even as a junior faculty. The committee that determined science was to determine science requirements because Yale students basically didn't have to take science,
mm,
which is not surprising for Yale.
mm,
And and
mm.
and, and so we tried to sort of double or triple the science requirements.
I see.
And we wanted and the computer science department desperately wanted computer science to be an introductory science requirement. We said no. We
Mm,
want an experimental science. And
mm.
so I remember saying what we could make it a foreign language requirement.
Mm.
So Fortran or what do you but
I
now I
see,
realize
right.
how completely well at the time it might have been true that the computer science in 1980 was not, but at least for undergraduates. But it's certainly now that I read your stuff, I realize how wrong I was about.
Well, look, part of what computer science majors learn is languages, but actually, there's a lot of complaints about the computer science major. That it doesn't prepare people for optimally for careers in tech because there's too much theory, too much ideas,
Yeah,
and
yeah,
not
instead of
enough
enough
hacking.
languages.
But that's what it is, right?
Yeah, but you don't need
It's not the
as the
only.
12-year-olds who start companies show, you don't need to go to college to
Yeah,
learn
yeah,
about
right.
technology.
I think a lot of fields have this conflict,
Yeah, yeah, yeah.
yeah.
Now, okay, so you chose math rather than computer science. Now, I mean computer science rather than math, and I understand was to get away. By the way, that's why I chose a degree in math because because it allowed me to skip doing an experimental physics class. So just so you
That's
know, and now
funny.
I kind of
No,
regret it.
the other thing, I realized that I wanted to prove theorems, right? I like proving theorems, but then there's a question of which theorems, right? And in
Mm.
math, what you have is you have such staggeringly high towers of abstraction, right?
Yeah,
That even to
unbelievable.
get to where the frontier is, even to understand the questions that are being asked at the frontier, right, could take years. And
Yeah,
then when you finally reach that point, then it's very hard to explain to anyone who's still at the bottom, right?
yeah,
And
absolutely.
I feel like theoretical computer science in a way was much younger. Like the questions were much easier to understand,
Initially,
and which didn't make them easier.
yeah, yeah,
God,
yeah,
P versus NP seems to be as hard as anything that's
yeah. Well,
ever been asked, right?
it's pretty hard. We'll get to it.
Yeah, but at least and you sort of see this. There are these 7 Clay Millennium
Yeah,
problems,
yeah,
right?
yeah,
That you get the $1 million prize for, right? But when people try to popularize them, they inevitably end up focusing on P versus NP, right?
yeah,
Because
yeah,
it's the one of the 7 where you can explain to anyone on the street,
yeah.
like
You can.
why how could an answer to this question change civilization?
Yeah, well, I hope
Right.
so. We're going to get you to
Yeah.
explain that
Yeah,
in a
yeah,
minute,
yeah,
and
yeah,
but not.
yeah,
I'm
yeah.
not going to get you to explain the Poincare conjecture or something. It's already solved, so it's
That's
passe.
that's the one that's solved. Yeah.
Yeah. So you went from from an undergraduate. I'm almost finished with your life story before we get to the science,
All
um,
right.
but I find it fascinating. You went to Berkeley, an interesting choice,
Yes.
and you decided to work on quantum computing. Was
Yes.
that because of your because you? Let me. I maybe I'll ask a leading question, as a lawyer would say.
All
Was it
right.
if I think about your interests now that I know them, which are
Mhm.
really in computation complexity, was it because quantum computing was sort of the most exciting way to actually empirically kind of address that problem, or was it something else?
Well, it was this new emerging field that sort of brought together computational complexity with some of the biggest questions about physics.
Uh-huh.
Is quantum mechanics, really true all the
Yeah,
way up to macroscopic scales,
yeah, yeah,
right? And how should we think about quantum mechanics, right? Should we believe or disbelieve in the many worlds interpretation? And I think I first read about quantum computing in a popular article around 1995, like, just shortly after Shor's factoring algorithm was
Uh-huh.
discovered, right? And it was about that, and it was saying, the usual wrong things that
Yeah.
people still say about Shor's algorithm today. They say, it works by just trying every possible divisor in a different parallel universe, and then, magically you get to pick the best one. And my first reaction when I read about this is like, this sounds like garbage. This sounds like some physicists who just don't understand what they're up against. That,
Which it was
like,
probably.
yeah,
Or it
well,
could have been an English
that,
major too, and of course it was right.
yeah, no, like they don't understand, the church Turing thesis, right? That all, different, laws of physics can all, reasonably well simulate one another. And it must be some phenomenon of some small number of particles that they're just illegitimately extrapolating to a large number. But of course, I had to learn something about it,
Yeah,
right? So
sure. That's great.
I the web itself was not that old, but there were already websites explaining Shor's algorithm and Grover's search algorithm, which had sort of just been discovered, for searching a list of n items and only square root of n steps. And what really struck me was that, like, I had read popular books at this point, that said, quantum mechanics involves waves that are somehow also particles, and they change when you look at
Yeah.
them, and you shouldn't even try to understand this. It's, it defies any, and I said, oh, okay, fine, whatever. I guess I'm never going to understand that, right? And then as soon as I started reading about quantum computing, it was completely different. They said, look, here's the deal. The state of a system is this unit vector of complex numbers.
Yeah.
And they're kind of like probabilities, but they're not probabilities because they're complex.
Uh-huh.
You can turn them into probabilities by taking their squared absolute values, right? That's what happens when you
Uh-huh.
make a measurement. But when you don't make a measurement, then this vector of amplitudes just undergoes this, linear transformations, these unitary transformations that preserve their norm. And I said, wait a minute, like I understood that.
Yeah.
Why didn't anyone tell me that before? and
Well,
uh,
yeah. Well,
and then with a little bit more than that, what are the basic rules of a quantum computer? And then, in some sense, you are playing the same game as, even, someone who spent their life doing physics, right?
yeah.
You know the same rules that they know. I mean, yes, the physicists may, have all sorts of intuitions that come from scattering theory, and that will let them think of, quantum algorithms that you can't, right? A great example of this would be Ed Farhi, who was my
Uh-huh.
colleague at MIT for
Yeah.
9 years, right? And he worked with Jeffrey
Yeah.
Goldstone
Yeah.
and others, right? And they really invented quantum algorithms that I would never have been able to invent by leveraging their knowledge of particle physics, right?
Mm-hmm.
But on the other hand, as a computer scientist, I might know things that they don't know, right? And I can bring those to bear.
Sure.
And
That's what's great
just
about.
understanding that there were these clear axioms. I mean, philosophically, how should we interpret them? What do they mean? People still argue about that, right?
Yeah, we'll talk about that. Although I'm not sure the
But yeah, but
arguments.
but uh, but 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 once you learn the axioms, then in some sense you can argue about those things too, as an equal of anyone, right? And it's true that there's a vast amount of physics, beyond just the axioms of quantum mechanics, but in some sense, um, it's kind of like with classical computing, right? You can know the rules of how a Turing machine works. That doesn't mean that you understand Windows. That doesn't mean you
Sure.
understand all of the software frameworks that were built on top of it, right? But like most of physics is just application software that is installed on the on the
on the axiom. That's
the
why we say shut up
underlying,
and calculate. We know what they are, and
yeah,
you just and you use that
yeah,
exactly
yeah,
what you
yeah,
just said.
yeah.
Unitary transformation.
And that was not at all the way that quantum mechanics was taught in to physics majors, right? Certainly
Uh,
not at that time.
Yeah, yeah, sure.
I think it's finally changing. It's starting to change now. But if I had been a physics major, I would not have learned it that way, right? What I would have learned was the historical order in which
Yeah,
the
thanks.
things were discovered, which means first you master classical mechanics, and you learn about thermodynamics, you learn about classical field theory, and then you learn this whole the whole Shaggy Dog story of
Hmm.
all of the anomalies that were discovered between 1900 and 1925,
Yeah,
like until people finally figured out what's going on, that okay, states are vectors of complex numbers, right?
yeah, yeah, yeah.
And
No.
in quantum information, we do it a completely different way,
Well, yeah,
right? We just
it's
say,
ahistorical, but
let's assume, let's grant that the experimentalists did a good job, and they, and let's try to understand, what did they discover, and how do we make sense of it?
yeah. To be fair, I think I don't want to belabor this, but to be fair, I think
Mm.
it's often taught that when quantum mechanics, because quantum mechanics is so hard to understand, that you kind of feel you want to lead students gently
Yeah.
into it to show why physicists were
Yeah.
dragged kicking and screaming,
Right.
and they
But
just
it's
didn't
kind
invent
of
this
like,
craziness. Yeah,
sometimes the best way to get used to a cold pool is to just leap in,
jump in. I know, I know. In any
Right.
case, some people have
Yeah.
argued. I remember a friend. I remember at one time in Toronto, he argued he was, and they tried. It
Mhm.
was abysmal failure to teach quantum mechanics before classical mechanics because
Hmm.
you don't need.
Right.
In fact, I never understood the.
Well, okay.
I never knew what a Hamiltonian really was until I did quantum. I mean,
Right.
really
Well, the thing
understood
is,
it.
like, I first knew a Hamiltonian as just, the instantaneous time version of a unitary
Yeah,
transformation,
absolutely.
right?
There you
The
go.
thing you exponentiate to get unitary evolution. And then I had to go back and learn what it had to do with energy.
Okay,
Right.
well, that's
And
good. Okay.
where it came from in classical physics, right? But I mean, I think the danger in learning things, in starting with classical physics, is that then you're always thinking about quantum mechanics as a sort of correction
Well,
to.
we'll come back to that because I think
All
that's
right,
part of the
fine.
huge problem. You
Yeah.
wrote a whole long article
Hmm.
for philosophers, which shows more
Hmm.
patience than I would have.
Hmm.
Um, and one of the big arguments is interpretations of quantum mechanics, which I would argue is just a big waste of time. But
Well, sometimes I feel like it's a waste of time, and then other times I feel like, well, look, Bell was driven to discover the Bell inequality by obsessing about Bohmian mechanics,
yeah, yeah,
right?
yeah, yeah,
David Deutsch was driven to, propose quantum computing by obsessing about the many worlds
yeah.
interpretation. So
And you like me
I think
both.
philosophy, a philosophy can be used,
Yeah,
as a
philosophical
springboard
questions can
into
be nice
science.
springboards, but
Yeah, yeah,
then you get away from them, and then you don't try.
mm,
Then you don't harp on many
yeah.
worlds. You point out. We'll talk about.
All
You
right.
like me think that his fixation with many worlds is misplaced because, well, we'll get there maybe because
All right,
I've
fine,
talked
fine.
about this in the context of quantum
Sure,
mechanics.
we
It
can
was
go
Sidney
there.
Coleman at
Sure.
Harvard who'd really
Mhm.
convinced me, that this was the world is quantum mechanical. Why talk about trying to interpret it in terms of classical mechanics? We don't do that with anything else. But before we get there, um, the there actually was. Oh yeah, but by having the way you learned it, what's really useful. I just had a podcast with a well-known biologist the other day, and he had
Hmm.
learned quantum mechanics incorrectly. He thinks quantum mechanics is indeterministic, which it isn't. It's just the linear equation.
Well,
It's
I
just a
mean,
second order
it
differential
depends on
equation moving forward
it,
deterministically.
it depends on at what level you look at it, of
Yeah, I know,
course.
but fundamentally, it's a deterministic theory, which is a unitary, nothing more
If
deterministic than unitary
certainly if
transformation.
you are a many worlder or a Bohmian, then it is. But yeah.
Anyway, well, I don't think you have to say that to do that, but we'll get there. Okay,
All right, all
you
right.
went to the Institute for Advanced Study right after your PhD.
I
Who did
did,
you
yeah.
talk to? I mean, I was there for a while, and there wasn't was there a quantum computing group, or did you talk to
So,
mathematicians?
well, not exactly. There was there was and still is one of the leading theoretical computer science groups, and it's led by Avi Wigderson,
Oh, okay.
who I had known. I'd actually spent a semester with him at that point at the Hebrew University in
Oh,
Jerusalem. and
Oh,
then he moved. He was in the process of moving to Princeton, where he still is, and he's in the School of Mathematics. So I was part of his group,
in the school of
and
mathematics. Okay.
yeah, and it was in it was a very tough decision. I also really liked the idea of going to Caltech
Yeah.
and working with John Preskel,
Yeah.
but a large fraction of theoretical computer scientists go through Avi, right?
Okay. Okay.
Go
That's
through
now I
Avi
understand that. Then you went to
at IAS,
MIT.
yeah, and but I did talk to I actually gave a talk there about quantum computing that I was hoping the physicists would come to, but the one who came was Pete Hutt.
Oh,
Uh,
Pete Hott, who's all, yeah, he's
yeah,
interested
yeah,
in
yeah. So
everything.
I did get to know Pete Hutt a little. I did talk once to Maldacena, and I was trying to that this was like 2005, right? But I was trying to see what might string theory say about computational complexity, and
Yeah.
he was reminiscing about it with me recently, right? He was saying like, yeah, there was this crazy kid, thinking that like quantum gravity and complexity theory were going to come together. How do I get him out of my office? I mean, he was actually very nice. He was very polite, but of course, this was a decade before this integration really started to happen.
Yeah, yeah, no, no. Well, yeah, I
Yeah.
was wondering whether Ed or well, actually Freeman Dyson, I would have thought might have come because at least he was
Yeah, no,
interested
I
in
mean, in retrospect, I wish that I had been bold enough to talk to Ed or to talk to Freeman Dyson,
but
and I wasn't.
okay. Yeah, when I was there, I
Yeah,
those are the two I knew, but I didn't hang out with the
huh,
string theorists. So Freeman
yeah,
was the one I spent time with because he didn't talk to anyone. I mean, he talked to
mm,
people, but he was right in the
yeah,
middle, and
yeah,
he was
yeah,
fascinating. But
yeah.
you went to MIT, which of course is a natural place to be, and
Yeah,
I
yeah.
was a
I also had two
MIT was
years at
there.
the University of Waterloo, and that
Oh
was
yeah, that's right, University of
yeah,
Waterloo.
that had an institute for quantum computing. Yeah, so
Yeah,
I went there, and
yeah, they were quite pressing in
that
that
was yeah
direction.
that was very important 2 years in my career, and then yeah, and then after that, yeah, I was lucky enough to get a faculty position at MIT. So and that's where I was for 9 years.
Yeah, and then I wanted to ask, because I mentioned you're not the first person I know who left Boston for Austin. A lot of my colleagues did when I was at Harvard and other
Mm,
places. And well, as you mentioned, Steve Weinberg was the first of the bunch
of
to
course,
make that.
yes,
To make
and he
that,
was he was actually involved in recruiting us to
I
Austin.
wouldn't be surprised.
Mm,
I mean, I would be surprised if it wasn't the case. Steve is a hero, and amazing. I used to visit
yes.
Austin regularly to see him, just to
Ah,
see him. Probably the only person I used to see there. Um,
mm.
but why did you move? Was it because they created a center for quantum computing, or was it?
Well, I mean, the immediate thing was just that my wife and I had a two-body problem to solve.
That's why he moved to Austin as well. Okay,
Yes,
it's a great
yes,
way to get good people to solve
yes.
that two body
So
problem.
yeah, so we did a search together, and the options that we had. I mean, we were lucky to have options at all, but they ended up being four big state universities. It was Michigan, Maryland, Illinois, or Texas, and so we looked at all of them, and to tell you the truth, I never would have imagined living in Texas. That was
Yeah,
just not
yeah,
on my not
yeah,
on my radar at all.
yeah.
But we like Texas the most. We like Austin as a
Austin's a
city.
nice town.
We like the computer science department here. They didn't have much in quantum computing, but they wanted to build something. And they had a very strong group in theoretical computer science. Also, I should say my wife Donna is also a theoretical computer
Ah,
scientist.
okay.
And,
That's the same
and they were
thing.
very strong in the kind of stuff that she does. And so this just ended up being what we chose.
Okay, yeah, yeah. And
Yeah.
they did make you a director right away of this quantum information center, which I assume is an attraction with resources, I guess. I mean, that was
Yeah,
where
I
I
mean, we
moved.
could, you're reminding me that I'll need to get more resources, but
Yeah. Okay.
but
Anyway, yeah,
yes.
yeah. No, you'll need and now
Yes.
once the universities give you resources when they think you may leave, and that's what I've always found. So maybe they think you'll go to OpenAI and they'll give you more resources. In any case, in the rest is history, and I notice among your prizes there are groundbreaking contributions to quantum computing. And and those groundbreaking contributions probably the reasons we first met with the Waterman Prize, to come full circle. And which I see behind you, because I have mine up on my wall, and
Right.
I see
Yeah,
it
yeah,
right
that's
back there.
right.
Mine looks
Yes.
very similar.
Oh,
And
yeah.
yeah, we both
There
got
you
them
go.
sent to.
Yes.
Okay, so let's start with quantum computing. And
Sure.
there's so many places one could go, but why don't we talk about? I want to get to shore at some point, but why don't we talk
Mhm.
about what it is and what it isn't? Because you're absolutely right. I look, I'm guilty when people ask me quantum computing, of saying, well, an electron can be doing many things at the same time, so you can do parallel calculations, and instead of one calculation, it's a simple way of saying what happens.
Yeah.
And you point out rightly that that's not it. But why don't you talk about what quantum computing is and what it isn't, and I may interrupt you with questions in the
Sure,
interim.
sure. Yeah. You can see why people fall for that, because the actual reality of what it is I think is weirder than any science fiction writer would have had the imagination to invent.
That's what's
Right?
great about science. It's
It's
usually weirder than
yeah,
fiction.
exactly. And the way that I think of quantum mechanics is that it's a generalization of the rules of probability. Right? So like you might think that it's just an axiom of math, that that it's not even physics, to say, look, if you want to know the probability that something happens, like that a particle reaches a certain point, then the way to get that is you add up the probabilities for all of the different ways that the particle could have gone to reach that point, and you see what's the total, right? And then quantum mechanics comes along and says, no, that's not true. Right? There's actually the way that nature calculates probabilities, at the fundamental level, looks very different from that. Okay, and it
Well, not
involves a
that different.
different.
It's just a complex number instead of a real one.
Well, yeah, that's right. That's right. That's right. But there's one change,
Yeah.
and everything else is the downstream consequences of that one change to the rules of probability. Okay, and the change is that now we have to deal with these numbers called amplitudes, which are complex numbers. Um, although actually, most of the stuff we care about in quantum information, you would already see just with positive and negative real numbers,
Yeah, you
right?
could already
You know,
see.
so
But
yeah,
I'm going to interrupt.
but the important point is that they have signs, right? They have not just a magnitude, but they have a
They have a
direction
sign.
as
And let
well,
me
right?
let me step back
They,
for the
yeah,
people.
yeah.
I don't anyone will have gotten this far if they don't know, haven't ever heard of a complex number, but just for
Mm,
people who know, yeah, they're numbers that are more complex. Because they involve the square roots of negative numbers.
mhm,
But effectively, it allows you a much more a much more um, rich way of adding up things. Instead of just plus and minus one, you have all these other options for adding things away,
mhm.
and that's what makes it richer. So I just wanted to step back so people kind
Yeah,
of
yeah, yeah,
understand.
sure, sure. Um, complex numbers were discovered by mathematicians in the 1500s, right? And I think it would have blown their minds at the time if you told them that nature actually uses these things, that
Yeah, it still
at
amazes
the
me. I
deepest
remember.
level, that they're not just a human invention, right?
Yeah,
but
I mean, all of
but that
sciences requires them. It's amazing.
Yeah,
I
yeah, yeah,
remember the
that's
first time I
right, that's
realized that.
right. But so basically, the key. Well, we touched on this before, but the key thing that quantum mechanics says is that if I want to know how likely something is to happen, like a particle is to hit us to be observed at a certain spot on a screen, then number one, I have to add up amplitudes for all of the different paths that it could have taken to reach that place. And then number two, I take the total amplitude, and then I take the square of its absolute value. And that tells me the probability. Okay, but now the big implication of this is, let's say that the particle could reach a place one way with a positive amplitude and another way with a negative amplitude. Okay, then those two contributions can cancel each other out so that the total amplitude is zero. And that then means that the particle will never be seen there at all. Okay. Whereas if I closed, and I mean, I'm saying this, not for your benefit, but
Yeah,
for
okay.
people
No.
who haven't heard this before,
Yeah.
if I close off one of the paths that the particle could take, now I only have a positive contribution or only a negative one, and now the particle can be seen there, right? So by decreasing the number of paths that a particle could take, I can increase the chance that it ends up somewhere, right? This is the part that has, no analog in
That's
our
the
classical
basis of the famous
experience.
double slit experiment.
Exactly, exactly. And now, what's you could say like the craziest part of all is that now if I just watch the particle as it's going to just see which path it's going, then I don't get this interference anymore, right? Then the different options just add up in just the same as they would in classical
Well, you
probability.
just got rid of
It's
some of
only
those negative paths. That's what you're saying. And once you
Exactly,
get rid
right,
of
right.
them,
It's
then the
only
particle
when
can now
I
be there.
right. It's only when I leave the particle isolated from the whole rest of the universe that I see this summing of amplitudes that leads to this interference. Okay, so interference is something that particles somehow like to do in private. They don't like to be seen while they're doing it, right? Okay, so now what's a quantum computer? Well, to say that, we have to say the basic building block of it is just going to be the quantum version of a bit, what we call a qubit, right? And
Mhm.
what's a quantum? What's a qubit? It's just some bit that has an amplitude for being 0 and an amplitude for being 1. Okay, so it can be in, as we say, in a superposition of the 0 state and the 1 state. Okay, so mathematically, we could say it's a unit vector of complex numbers, right? It's two complex numbers, amplitude of 0, amplitude of 1. Um, but now, if I have, let's say, 2 qubits, right? Then I can't just write down amplitude separately for the first qubit and for the second qubit, right? I have to, because measuring 1 qubit might tell me something about the other qubit, right? And so there are 4 possibilities for 2 bits: 0, 0, 0, 1, 1, 0, and 1, 1. Right. And we've known for a century now that quantum mechanics forces us to write down an amplitude for each of those 4. Right. But now it gets worse, because if I have 3 qubits, now there are 8 configurations of 3 bits, from
Mhm.
0, 0, 0 up to 1, 1, 1. And so now I need 8 amplitudes. If I have 100 qubits, now I need 2 to the 100 power amplitudes, right? 1,000, 2 to the 1,000 power amplitudes. And now already we have more amplitudes just to describe our 1,000, little particles than there are atoms in the observable universe, right? And so, and this has been a core part of quantum mechanics, since Schrodinger, wrote down his equation in 1926. Right, he was
Mhm.
very explicit about this. Like, if you read his paper, but in some sense, it is only with quantum computing that the full staggerings of this is really brought to bear, and that we're really trying to exploit it to do something, right? So quantum mechanics is sort of has been telling us that just to keep track of the state of 1,000 measly particles, nature off to the side somewhere has to maintain some scratch paper,
Mhm.
with more parameters than you could write down in the entire visible
Mhm.
universe.
Yeah.
And every time something happens to those particles, it has to cross off all of those parameters and replace them with new parameters, right?
Yeah.
So that's a ridiculous amount of work for nature to be going to, from a computational standpoint, right? Just
Mhm.
to keep track of what 1,000 particles are doing. And chemists and physicists have, in a sense, they've known this for a long time. They've known it mostly as a practical problem,
As a
right?
practical problem, if they want to
Yeah.
try and understand even a small molecule, you have
Hmm.
to calculate so many things to try and
Yeah.
understand how quantum mechanically how a molecule behaves, much less a nucleotide or a DNA or a protein.
No, absolutely. I mean, so they've known that there's this exponential explosion in the number of parameters you have to keep track of. This is why, very powerful, supercomputers, including, one we have here in Austin called Stampede, are often used for just trying to solve the Schrodinger equation, trying to, simulate complicated quantum systems. And people have gotten very good at inventing approximation methods and shortcuts, that sometimes let you manage it, but but sometimes not. And
And
so it was not until the early 80s, I would say, that a few physicists, most famously Richard
Rich, I
Feynman
was going to, you're
and
leading
and
into
and and
Feynman, of
and and,
course.
and then David Deutsch,
Yeah.
started saying, well, if nature is giving us this computational lemon, then why don't we make lemonade,
Yeah,
right?
yeah. And
Why
Feynman
don't we
basically said maybe he could help him understand quantum mechanics, which is always
Yeah,
an
exactly. So why don't we build a computer that itself, would be made out of qubits that would exploit, this exponentiality of amplitudes? And well, supposing you built that quantum computer, what would it be good for? Well, Feynman really only had one answer 40 years ago, which is it would be good for simulating quantum mechanics.
Yeah, I mean, and just
And
let's step. I mean, that
yeah,
was what
yeah,
excited him. And let's step back. What he said is, look,
yeah,
I can't calculate. I can calculate. I know how to calculate the answer to this problem, but I can't physically do it. But if we use if the calculator itself is quantum mechanical, it can do it in a way I can't do and get an answer. And yeah, for Feynman, that was, and he was way ahead of his time, of course,
yeah.
but as
Mhm,
always, but
mhm.
or often, not always. Um, yeah, and he said, yeah, let's make, maybe we can make quantum computers so we can solve quantum mechanics problems that I can't solve. And then maybe
Yeah.
I'll better understand quantum mechanics. I'll
Mhm.
understand the aspects of quantum mechanics from interference and other things. Yeah, I wrote
Yeah,
a biography of
yeah.
Feynman, so
Now,
that's,
right now, it's important to say a quantum computer wouldn't be able to do anything that's literally uncomputable with a
yeah,
classical computer, because if you had enough time, then with your classical computer, you could always just write down the
yeah,
entire list of amplitudes
yeah,
explicitly.
right.
But that could be exponentially slow. I think that simulating quantum mechanics is still today, 40 years later, after everything that's happened, it's still the most important economic application of quantum
Yeah,
computers that we have.
let's stop there for a moment
Yeah.
because it's a fascinating thing to say that in the end, and I agree, and it's something I think that
Hmm.
that
Hmm.
Dressler and I talked about,
But
because it's
right,
not what you
but
get in the media. The
yeah,
media
that's right. That's
suggests
right. You're
otherwise.
absolutely right. Right, but that was not what put quantum computing on most of the world's radar.
It was
And
something
what
Peter
what
Schroeder.
what put it well what originally put it on most of the world's radar, including the computer science community,
Yeah.
and the math community, was a sequence of discoveries in the 1990s that culminated in showing us that a quantum computer can sometimes get enormous speed ups over anything we know how to do with a classical computer, even for solving problems that have nothing to do with quantum
Quantum
mechanics,
mechanics.
purely classical problems.
Yeah, in
Okay. And
principle.
the famous example here is finding the prime factors of enormous numbers, which for better or worse is a problem that much of the security that protects the modern internet is based on.
Well,
Is based
let's
on
face it. In
the
my, I
belief
mean,
that that problem is hard.
I
But
watched this from as an outsider. I watch it explode
mm,
after that,
yeah,
and
yeah, of course,
it's kind of
of
fascinating.
course.
It's the same, but it's interesting. The reason that that particle physics and
Hmm.
exploded, and it was because they could build atomic bombs, and and the defense of the nation seemed to be okay. We'll throw as much money as this as you want. But maybe there's other things you want to do, but we're interested in it for this reason. And it was amazing to see. I think the first, I could be wrong, but from an outside, it looked like the first group to start funding was defense for the same reason. That if you could
Mm.
factor large prime numbers, you would be able to crack the
Large
world
composite
financial,
numbers, but
uh,
yeah,
and therefore we're
yeah,
going to throw
yeah,
as much money as possible at this field. And you can worry about your other physics questions, but
right.
we're interested in
Well,
that.
I mean that was certainly the discovery that made the military and intelligence communities interested in this,
And
right?
money,
The,
about money.
but interestingly, and unlike with the atomic bomb, I guess they are not the main ones driving it now,
Now,
right?
not now, but
That's
got the
right. That's
money
right. That's
involved,
right.
and
That's
then
right.
yeah,
That's right. That's right. Now, the main ones driving it are private companies, who are hoping that it's going to be a massive accelerant for AI and machine learning and
Yeah, exactly.
finance
It
and
moved on to other things, just as
optimization,
particle physics
and
moves.
those and those claims are often very iffy ones.
Yeah, we'll get there. They're very iffy. That great hopes.
We can get into that. But what I wanted to say was that the way that almost every popular article will explain quantum computing, still to this day, is just by saying, well, a classical computer with classical bits can only try the possible solutions one by one, right?
Mm-hmm.
And if there's an astronomical number, then that could take longer than the age of the universe. Whereas a quantum computer can just try all of them in parallel, in superposition, and that's the source of its speed, right? But that kind of sounds too good to be true, right? It's like, wait a
And it
minute,
is.
I just get this magic machine that lets
Mm.
me, try everything in parallel, right? And it turns out that that is too good to be true, right? And that was one of the earliest things that people had to understand, is that the only hope of getting any advantage at all from a quantum computer is to exploit the way that these amplitudes, being complex numbers, are different from probabilities, right? And specifically, it's to exploit this effect of interference. Okay, so basically, I think the right way to think about it is that with every algorithm for a quantum computer, we are trying to choreograph a pattern of interference, right? And we're trying to make it so that for each wrong answer, each one that we don't want to see, some of the contributions to its amplitude are positive, some are negative, or at any rate, they mostly cancel each other out. They're pointing every which way, right?
Mm-hmm.
Whereas for the right answer, the one we do want to see, we want all the contributions to its amplitude to be mostly pointing the same direction. Okay, and so that they all reinforce each other, right? And if you can arrange that, then when you make a measurement, quantum mechanics tells you you're going to see the right answer with a high probability, right? Of course, a high
It's a
probability is
beautiful
all
way
you
of
need. If you
explaining
don't get
quantum
it, you
physics.
can always try again until you get it, right?
Because
But
because I think,
yeah.
I mean, it's a beautiful explanation, but it also emphasizes something else that I know I've learned
Hmm.
from your descriptions. I think
Hmm.
that what people don't realize is that you end it, there may be all these qubits, but you measure something in the end, and so you get
Yes.
a number out at the end, and
That's
so
right. That's
where do you
right.
get all these
There, so,
parallel
so
calculations?
you could say in some sense, this exponential amount of information was there, quote unquote,
Yeah.
what I call this giant scratch paper, with
Uh-huh.
all of these parameters, but we never directly see them, right? And you could ask, if we never see them, how do we know that they were ever there in the first place, right? Well, we know that we need them to calculate the probabilities of the different things that we do see, right?
Yeah.
But when we look, then all we see is, if I have n qubits and I
Uh-huh.
measure them, then all I see at the very end is n classical bits.
Yeah.
And the whole game is to choreograph the interference pattern so that those classical bits are the ones that I want, the ones that solve my problem, right? And
Yeah.
now the hard part is, I have to choreograph this whole interference pattern that magically concentrates amplitude on the right answer, even though I don't know myself in advance which answer is the right one.
Yeah. Yeah.
If I knew that, what would be the point,
Yeah.
right?
Yeah.
And I have to do it all faster than a classical computer could do the same thing. Or else again, why
What's the
didn't I
point?
just do it with a classical computer, right? So, nature gives you this really bizarre hammer, right? And it's not obvious whether there are any interesting nails that hammer can hit,
Yeah.
other than, maybe simulating quantum mechanics itself, right? And that's why, it was really a non-trivial discovery, in the 90s, that there are classical problems where we can figure out how to, design this interference pattern, shape it in the right way. Like that took more than a decade after Feynman for
Yeah,
people to
sure. That's
discover
when
that.
people
It was
got
not
excited. Now,
obvious.
you have given,
Yeah.
and I've read I think probably the first time I really understood, I must admit the real time. Yeah, first time I really understood Shor's algorithm, was
Hmm.
reading your explanation of it.
Yeah.
I'll be open and say that. I don't know whether, so
Thanks.
the problem is easily framed. Once again,
Hmm.
large, it takes longer in the age of the universe to take a very large number and find the prime factors of that very large
Well,
number.
it might. No one,
Well, I
no, no,
mean, no, it
no
might.
one has proven that, right?
Yeah, okay,
You know,
that's right. And so
I've talked to
far,
I've even talked to mathematicians who strongly believe that there is a fast classical way to do it. But you know, but the reality is no one knows.
well, you know
Right?
what's interesting?
Yeah, yeah,
I will tell you this as a physicist, maybe something,
yeah.
an analogy that you haven't heard before.
Mm,
Um, I'm amazed that you don't take things seriously until they've been measured. And
mm,
so, um, uh, I've written a lot of papers about stuff that I could have written before, but I never really thought about it until some experiment came along and thought, oh,
yep.
and the interesting thing is when we get to quantum supremacy, that it was only after sort of this claim of quantum supremacy, it seemed to me, that people started to realize, oh, I've got a classical algorithm that's actually much
Mm.
faster because I'll take it seriously. And you're right,
Yes, no, this sort of thing has happened. I mean, there have even been interesting new classical algorithms that were only discovered because people were first thinking about quantum algorithms,
absolutely. I
right?
think
And
it's
then
interesting.
how
I
do
think
you
it's fascinating how that
dequantize
happens.
them?
But
Yeah,
in any
yeah,
case,
absolutely.
let's step back.
Hmm.
It
Hmm.
may be that it takes long. Apparently, if you don't think
Yeah.
hard enough, it takes longer in the age of the universe to do to empirically find the prime factors because you'd have to try every prime factor in a big
Mhm.
number. It
I
just
mean,
takes
we
too long.
know methods that are somewhat better than that, but they're still some
Yeah,
kind of
yeah.
exponential. The
And then
best methods, like the ones that the NSA is presumably using to, try to, break, cryptographic keys, they take an amount of time that grows exponentially with the cube root of the number of digits
Cuban.
in
Okay,
the
there we
number to
go.
be
So it's
factored.
exponential Cuban.
Anyway,
And
yep.
so what was a surprise was that there was a quantum algorithm that might allow you to um, find the prime factors of a large
Yes.
number that was only polynomial in the number of the size of the
Yes.
number.
Yes. Well, in 1994, Peter Shor proved a theorem, and the theorem says if you build a quantum computer, and if it works, like the theory
Yeah.
says, then it can, in fact, factor a number that's n digits long using a number of elementary operations that only grows like roughly like n squared.
Like n
Okay.
squared.
So that is exponentially faster than the
Okay.
best known
Now
classical
we've
algorithm.
taken a long time already, and we've got a lot left to do. So I don't know if I'm going to ask you, and you may not. I mean, I've read your argument. It would
Hmm.
take 10 or
Yeah.
15 minutes. Is
Well,
there a simpler?
really, it's Shor's argument. I'm just,
Okay, okay, Shor's argument, but is there
explicating
a
it. But yeah,
simple?
yeah, yeah.
Is there a simple kind of 1 minute way of saying what the trick is or not? If there isn't, it's okay.
I mean, I can try.
Okay.
So the key is, it's there's a half of Shor's algorithm that's got nothing to do with quantum mechanics. Okay, where
Okay.
it's just about number theory, really. Okay,
Yeah.
where you're taking the problem of factoring and you're reducing it to a superficially different problem. Okay, and the different looking problem that you reduce factoring to is called period finding. Okay, so consider the problem where I have this enormous sequence of numbers, right? It could be like a sequence of a Google numbers, right?
Okay.
Whatever, right? But and this you're told that this sequence repeats itself with a certain period, right? So it's secretly a periodic function. Okay, you can compute any desired entry of the sequence,
Mm-hmm.
right? You have an algorithm that
Uh-huh.
given you ask for entry number J, it tells you what that is pretty quickly. But now your task is to discover what is the period, right?
Okay.
And so now we so what the first thing that Shor showed was that if you can solve that problem, then you can also factor, right?
Mhm.
And the reason, it's a few lines of algebra,
Uh-huh.
basically, right? It's but not having a board, I probably won't go through it,
Yeah, yeah,
right?
okay.
So, but it's the point is, a lot of interesting problems in number theory sort of can be boiled down to sort of finding this hidden periodic structure, in a periodic
Okay.
function. Okay, there's something called, if I have some composite number, there's something called the multiplicative group,
Mm-hmm.
modulo that composite number, all the
Mm-hmm.
numbers that are relatively prime to it. And basically what I'm trying to do is discover how many elements are in that group. And if I figure that out, then that also reveals to me what are the factors. Okay,
Okay.
so I'm
That's
trying to
interesting.
figure out the order of this group, and to do that, I have to find the hidden period of this periodic function. Okay, so now, how can we do that? Well, if I just had a classical computer, I could imagine that I just pick a bunch of random elements in the sequence, and
Mm-hmm.
I hope that eventually I get lucky and I find two elements that are the same,
Uh-huh.
right? And if I find two that are the same, then I know that whatever was the period of the sequence, it divides the difference between,
Yeah. Okay.
right, but that would take again an astronomical amount of time, right? So now, so here's where the quantum computing is going to come in. Okay, so now what Shor says to do, and he was directly building on earlier work by Bernstein and Vazirani. Vazirani was my advisor at Berkeley,
Uh,
and then Dan Simon, who
yeah.
did very closely related things, but they didn't solve a problem that was as high profile as factoring,
Yeah. Okay.
right? And then but now is going to come the step where we need to exploit quantum interference. So we create an equal superposition over all of the possible elements in the sequence, right? We calculate all of them in superposition.
Mm-hmm.
Okay, so now so far it doesn't look like we've made that much progress, because if I just took this superposition over all the elements of the sequence and I just measured it right now, if I was
Yeah.
impatient, all I'm going to get out will be a random element of the sequence,
Yeah.
right? And
Yeah.
I didn't need a quantum computer for that, right?
Yeah. You
Okay, so
can
now
pick a
somehow
random.
I have to exploit interference, right? And so what I do is I do a sequence of unitary operations on my qubits that has the effect of taking this giant vector of amplitudes, that encodes my periodic function, and replacing it by its Fourier transform.
Mm-hmm.
Okay, so now the Fourier transform, as but for the benefit of our listeners, it is one of the most basic operations in linear algebra, and really in has been central to quantum mechanics since
To all of
Heisenberg
physics.
wrote down the uncertainty principle, right?
Uh-huh.
But it's a linear transformation that sort of it's a change of basis that sort of moves you from looking at an engineer might say moves you from the time domain to the frequency domain, right? So it moves you from looking at your sequence just element by element to looking at it as a sum of periodic contributions,
Mm-hmm.
each of which has a different period. Okay, and so what you do is you do this short sequence of unitary operations, each of which acts on only one or two qubits at a time, but it has the effect of taking this amplitude vector, replacing it by its Fourier transform. Okay, and now the Fourier transform was designed from the beginning to reveal periodicity information, right?
Mm-hmm.
And so now you get like these giant, you get a new quantum superposition, but that has giant spikes at
Yeah.
numbers that they're not necessarily like the period themselves, but they're like close to integer multiples of inverses of the period,
Mm-hmm.
right? And so now you measure, and now you get numbers that are that if I just see a few of them, then just using my classical computer, I can put them together and reconstruct what the period of the sequence was. Okay, and a good way to think about what's going on here is that, like, for every possible number that I could have measured, right, I it has an amplitude that's a sum of many contributions, right? But only for the ones that are multiples of the inverse period, or very close to them, are all of the contributions to their amplitude adding up constructively? Are they reinforcing, right?
Mm-hmm.
For the wrong numbers, I have the contributions are just pointing every which way in the complex plane, and they're just canceling each other out. That would be, I don't know if that was like 3 minutes, or but
Or
that
maybe
would
five, but it was,
that would
and I think people get the
uh,
idea.
Yeah,
but
that would be that would be my summary of Shor's algorithm. I
it's a
mean,
great.
when I teach an my undergraduate course in quantum information, you can just do this in full details in about 3 lectures.
Yeah, it's really amazing.
Yeah.
But it demonstrates something. But now I want to get. And some people I'm sure got lost during it, but
Mm.
may not. Well, maybe no one did. But I suspect some did. But I want it. But it's important to talk about it because now when one of the things I think which is clear, you've already made clear, but people don't recognize is the world. I would say now, and this is something that took me a while to realize, and you helped me. Um, but over the years, it's when people talk about what quantum computers are going to be used for, I
Mhm.
would argue that that's as like that cracking financial codes or is going to be is not realistic in the near term. I'm not sure whether it's ever realistic in the long term, and it's probably
I
not
think
going to
it
be the
is.
number one
I mean,
activity of
okay.
quantum computers.
First of all, I think it is realistic in the long term. I
Okay,
mean,
well, it's
well,
going to require you if you have
it's basically. I think once you okay, so we haven't talked about the practical problem of how
the
do you
practical
build a
problem is how
quantum
do you keep
computer,
n
right? But
qubits going? I mean,
that's right.
if
That's
you have a
right.
big
How do
number,
you
you're going to need a large number of cubics. So that's what I wanted to get to
Exactly,
next.
exactly. So the main problem is that you need what we call error corrected qubits or fault tolerant qubits, ones that like I said before, quantum states are very fragile, right? They're like being in superposition is something that particles only want to do in private, when no one's
Exactly, and
looking,
that's really
right?
important. I want to emphasize
And
that because people don't get it when they see
mm,
the difference between quantum mechanics and classical mechanics or the
mm,
exploitation of quantum mechanics at a macroscopic level requires something that's very unnatural for
mhm,
particles or anything. The reason we're not quantum mechanical or don't behave quantum, we are at some fundamental level, but we don't behave that way, is that we're a mix mash of particles interacting with all thing with each other in my body and all the
yes,
photons from the lights that are,
yes,
and it's
and
all
everything's
washing out all
constantly
of those
measuring everything
interferences that
else.
make
Yep.
quantum mechanics so special. And that's why we don't ever see it. And so what
Mhm.
you've got to do if you have a bunch of these, if you have if you want to have a large number of bits, I mean, my phone has a large number of bits in it, gigabits, and
Yes. Just
but
as
if I'm
mine.
going to have a large number, then I got to make sure somehow that large number remains quantum mechanical, and if
Yes,
it did,
exactly.
then I would be used to it. And so most of the time it doesn't.
Exactly. No, and you could say that that problem is so staggeringly difficult. How do you keep your qubits like, almost perfectly isolated from everything else in the universe, but then
Hmm.
also have them interact with each other, in this
Yeah.
precisely choreographed way, right? And, like something has to come in and tell them what to do, right?
Yeah.
It's so hard that there were distinguished physicists and computer scientists in the 90s who said this is fundamentally impossible, right? This is like building a perpetual motion machine or a Maxwell's demon or something like that, right? Like like maybe this works with a few qubits, but this can never scale to a large number of qubits, right? And I think a priori, like, okay, that was a plausible position, right? Sometimes you
Yeah.
can write something down formally that abstracts away some key feature of the real world that would actually make it impossible. But then there was a key further discovery in the 90s that convinced almost all of us that this is quote unquote merely a staggeringly hard engineering problem, right?
Yeah.
Not requiring any new physics. Okay.
Okay.
And that was this discovery of quantum error correction, quantum fault tolerance. Okay, Peter Shor was again, very involved in that discovery, and then a bunch of other people were as well. Okay, and it culminated, and basically what it said is that there are, in the classical world, right, when we have noise in a communication channel, right, we deal with it using error correcting codes. Right, and this goes back to Claude Shannon and
Hmm.
Hamming and many others, right? But for example, instead of sending either a 0 or a 1, I might send 000 or 111, right? And then if any one of the 3 bits flips, then I can still recover the message by just taking the majority of the 3, right?
And
And
exactly, and you could test to see whether one
yeah,
is. I mean,
right. And now that doesn't immediately work for qubits, because one reason is that you can't clone a quantum state, right? If you don't know what it is, there's no way to make a copy of a qubit, and also errors in qubits could be continuous, right? It doesn't just have to be a discrete bit flipping. It could be any little change to these amplitudes. And so some people said, well, this seems like an analog computer, right? And analog computers never, they didn't win in the end, right? And the main reason was error, was you would just have errors that would build up and kill you. I mean, that's why digital computing won. Okay, but the key discovery of quantum error correction is that there are these very clever quantum generalizations of error correcting codes, right? The first one discovered was called the Shor code, right? It encodes a single qubit, a single logical qubit into 9 physical qubits. Okay, and it turns out 9 is not the minimum. You can also do it with 5. Okay, but classically you needed 3, right? Quantumly, you need 5. Okay, and what these quantum error correcting codes do is that they allow you to make a measurement that only tells you, like, did an error happen, and if so, what do I have to do to fix it? And it doesn't tell you anything else about the qubit, which you don't want to know
You
more.
don't
You
want to
don't
know
want
because
to
you don't
know
want to
something
destroy
that would destroy the state. So that joke where, like, someone calls 911 and says, "Oh my God, this person was shot and was killed," and then they said, "Well, okay," and the dispatcher says, "Okay, but did you check to make sure that they're dead?" And then and then you hear a gunshot, and they say, "Okay, all right, now I'm sure.
Sure.
What now?" So quantum error correcting codes are kind of like that. It's like it's like if there was some tiny rotation in the amplitude, like, well, you could say, was that an error or was that not an error? Well, the way you decide is by making a measurement, right?
Yeah.
And the result of the measurement might be that it just snaps back to where it was before, and then okay, I guess there wasn't an error. Or the result of the measurement might be that it flips all the way, and then okay, well, I guess there was an error, but now the error was discrete because I measured and I made it discrete, right? And now I know exactly where it was, and I know what I have to do to fix it. Okay, so this whole line of work culminated with something called the fault tolerance theorem, or the threshold theorem, which said that if you want to build a reliable quantum computer, you don't have to get the rate of noise, the rate of interaction between the qubits and the external world all the way down to 0. You merely need to make it very, very, very small. Okay, but there is some non-zero rate of noise which is low enough that you can then use error correcting codes to push the effective error rate all the as close to 0 as you would like. Okay, so there is a threshold effect. It's kind of like the critical mass for a nuclear weapon, right? If you're halfway there, you don't get half as big an explosion, right? It's like you have to be able to correct the errors faster than you are introducing new errors, by trying to correct them. Okay, but there's some finite rate of error where this becomes a net win. And you could think of the engineering goal in quantum computing for ever since then, really for the past 25 years, has just been trying to get better and better control over quantum systems until ultimately you would pass this threshold of fault tolerance. And at that point, once you have fault tolerant qubits, then it really is just an engineering problem, right? Like, how many, you could have in principle as many qubits as you want, and they'll stay alive for as many operations as you want to do with on them.
Which is the holy grail. And now
That's right. And it is, if you look at the numbers, it's it doesn't even look like in a totally unattainable grail. I mean, when I entered this field, in like the late 90s, it would have been spectacular if you could do, a 2-qubit gate. So just, an interaction between 2 qubits that with like 50% accuracy, right? Or some number like that. Okay. And then that 50% became 90%, came 95, with Google's quantum supremacy experiment that it announced 4 years ago. They had like 53 qubits, and they could get any two neighboring ones to talk to each other with 99.5% accuracy, right?
For some short
Within
time.
yeah, that's right. Within the last year, groups like IBM, Quantinuum in Colorado are talking about 99.8%, pushing 99.9% accuracy. Okay. Now, our best estimate from fault tolerance is that if you could get this to 99.99% accuracy, then quantum error correction should start to work, should start to be practical. Okay, so if you just plot it on a graph, it looks like we're now only about one order of magnitude away. Okay,
Exactly, and
then
I should look. So it is nevertheless an experiment. Well, as you mentioned, with lots of money and lots of time, there's improvements, but it's experimentally at the limit of what we can do.
It is. Oh yeah. I mean, these are amazing experiments, but I mean, a priori, you might have worried that this would have to go on forever.
Yeah,
right?
no. In fact, I would say that
no,
I was one of the naysayers before fault tolerance. I was saying there's no way you're going to be able to get a quantum system to survive long enough to do what you want it to do.
Yeah.
And then now it's still a challenge to get it to survive long enough for enough qubits. But I guess my point is, so if you have 80 qubits, then maybe you can begin to do something realistic when it comes to the issues of cryptography. But what's needed?
No. You're gonna need a lot more than 80.
Yeah. Okay. Maybe a lot more.
So basically, people have gamed this out in a lot of detail at this point. So I mean, if you want something that's useful for breaking cryptographic codes, then you're going to need a few thousand logical qubits.
A few thousand. Okay.
And then with error correction, that's going to translate into millions of physical qubits.
Okay. So this is my point. I guess what I was trying to say, as a physicist rather than a mathematician, is you're right. I don't think there's any logical barrier. But my point, before we leave this area, or at least talk against the conventional wisdom, is that with 5 qubits, you can do really interesting quantum mechanical problems of molecules, and that's feasible. What I wanted to say is, if you're going to get to this realm, which one day we may get to, of doing things that are realistic cryptographically, well, already the world financial system will have adjusted that you could be doing
that's a different discussion.
Yeah, I guess all I was saying is, for those who think the world financial system is suddenly going to be broken, the time scale of quantum computing improvements with fault correction is such that it's not going to. May there be other problems it'll help with, but the world financial system will have long go past that by in some other way.
Yeah. So I did want to talk about these engineering issues, but I agree with you that breaking public key cryptography has never been the sort of it's first of all, it's far from obvious that it's a positive for humanity if you can do that, right? It's it all depends on who has the capability and who else knows about it. Okay, but second of all, we already know cryptographic codes that seem to resist attack even with quantum computers. Okay, now it's going to be a massive effort to get everyone to migrate to those new cryptographic codes, and the crypto community for the last decade has been pushing that, and the National Institute of Standards and Technology, NIST, just concluded a competition to come up with the standards for post-quantum crypto systems. The winner, as many of us had expected, are these public key cryptographic codes based on high-dimensional lattices.
So these systems exist.
they do require like larger key sizes, larger message sizes than the cryptographic codes that currently underpin the web. So, so they're a little bit annoying, but, they can be used, and people are already thinking about how to deploy them. So, if we succeed at migrating everyone to post-quantum cryptography, then, you could say, like in practical terms, Shor's algorithm could just be this colossal, scientifically fascinating nothing burger, right? It's,
Yeah.
it'll just, we'll just all be right back where we started, right? And so I think that, the biggest hope of doing, I mean, look, I mean, for me personally, the number one application of a quantum computer has always been just to disprove the people who said quantum computing was impossible.
Okay.
Right? It's
Or
always been to, yeah.
and by token, for me as a physicist, you might say the number two application is to demonstrate that quantum mechanics works
Yeah,
at
that's right.
macroscopic
Yeah,
levels.
we can collapse those into, basically the same thing, right?
It's really the same thing. It's
It's
different
just
sides of the
doing
same
that. Yeah,
coin, the
it's
same
like,
quantum coin.
it's like a quantum computer as the same sort of thing as, the LHC or LIGO or the James Webb Space Telescope. It's a, and it's, it's you're just probing nature in a new regime, and of course you want to do that if you can.
Yeah,
Right.
yeah. I mean,
But
there's
then,
some people like me.
and then I think the number two thing is to give us this general purpose programmable tool for simulating quantum mechanics,
Yeah.
which might be useful for designing new batteries or solar cells or high temperature superconductors or drugs.
Or drugs, or
But
understanding biological systems.
I mean, the truth is we don't really know.
We don't know till we do.
We
Exactly.
don't know what such a device would discover. But I think there's a pretty strong case that, yeah, that would be useful to have.
Yeah, and we know we don't know.
And
That's what makes it so
right,
exciting.
right, and then I think neither of those things is what has mainly driven the investment over the last decade, right?
Yeah,
The
yeah.
you know the reason why there's these billions of dollars being invested in quantum computing now by Google, Microsoft, IBM, Amazon, and then like I think hundreds of venture-backed startups,
Yeah.
at this point, right? It is, what people have mainly gotten excited about is the hope that a quantum computer would accelerate machine learning, optimization, financial
Yeah.
problems, AI problems. And here, as a quantum algorithms person, honesty compels me to report to you that the situation is much, much iffier. Yes, there are some quantum advantages that eventually, you should be able to realize for those problems. Okay, a lot of them derive from Grover's algorithm, which I mentioned before, which is maybe the second most famous quantum algorithm after
Mhm.
Shor's. Grover's algorithm can be used for sort of searching any list of n possible solutions in only about the square root of n steps. And so it has an enormously wider range of application than Shor's algorithm does. Right? Shor's algorithm is really, really specialized to
Mhm.
factoring, period finding,
Yeah.
and a few related problems in like group theory and number theory. Right? Grover's algorithm is for like, you can just flip through a computer science textbook and like, 2/3 of what's there could be Groverized in some way, right?
Okay. Okay.
So, it could be, be a workhorse for all kinds of things. But the disadvantage is that the speed up is not exponential. The speed up is only, quote unquote, by this square root, this quadratic
Yeah.
factor, right? And now that has to compete against the enormous overheads that it would take to run a fault-tolerant quantum computer at
Yeah.
all,
Yeah. So you
right?
got.
So it's like if you can take a problem of size n and solve it in, you can, like as theorists we'd say, Grover solves it with scaling that only grows like the square root of n. But in practice, that's probably something like 1,000,000 times the square root of n. Right. And
Yeah.
so now the point is n has to be big enough
Big enough
that
to.
1,000,000 times the square root of n is less than n. And
Yeah.
you
Yeah.
can
Yeah.
solve that, but n has to be pretty big.
Yeah. It
Right.
has to be pretty big.
So So that's the main issue with all of these speed ups based on Grover. And so then people say, okay, but there are all, we don't need an algorithm with a provable performance guarantee. There are all of these heuristic quantum algorithms. Okay. And so a lot of the excitement over the last decade has been driven by things like quantum annealing, which is like the quantum adiabatic algorithm, which I alluded to before. My former colleague Ed Farhi and his friends developed this, and these are like, there are these classical heuristic algorithms, that don't always work, often don't work actually, but often enough they do work. Okay, a famous example would be simulated annealing, right? Where I just start with a random solution and then I just keep flipping bits, if it looks like it's improving things, right? And I try to get to as good of a solution as possible. And so what people have done is that they've invented quantum versions of those heuristic algorithms. And then, and now here's what happens. Okay. Like as theorists, like, we don't know what the hell these things do, right? But we can't rule out the possibility that at least sometimes they might solve these AI or optimization problems exponentially faster than any classical algorithm, right? And so then the sort of, business people or the funding people, like that's all they need, right? Then they just be like, okay, so then let's just make the most optimistic assumption imaginable, right? Let's just assume that these will get these exponential speed ups for all of these problems, but now, you can see like there is not a case here that is anywhere near like the case that Shor's algorithm helps you with factoring, right? And in fact, what is turned out again and again is that when people have claimed to be able to use these heuristic algorithms to get huge quantum speedups, again and again people have been able to dequantize them. Okay, to say no, actually, if we think about it enough, we can replicate that sort of performance with a classical computer. Right?
Which is sort of what happened, and I want to leave quantum computing in a second, but which is sort of
Yeah,
what
okay,
happened with
sure.
quantum supremacy. Quantum supremacy, which the term coined by Presco, I guess, was
It was, yes.
is the idea that basically you've gotten to a point when quantum computers can do something, maybe not
Yes.
something interesting, but something in a finite time that a classical computer would take longer than the age of the universe. Well, there was a big report, 2019, Google,
Yeah.
and then IBM, as you might imagine, came up and said, "Hold on, actually we found out how to do it in 3 hours instead of 2 minutes or something like that." And
Well,
the class,
I should say something because I was heavily involved in this story,
yeah, I
right?
know. Okay, so
So
I
yeah,
introduced you, so you would.
my student and I in 2011, proposed one of the I guess the main ideas for how you would do these quantum supremacy experiments, right? And then a year later, Presco coined this term quantum supremacy to refer to things like what we had
Yeah,
proposed,
yeah,
right? Where you're not trying to solve something that is useful. You're merely trying to solve something that is well defined and that is classically hard,
yeah. Okay.
right? And it turns out that if that's your goal, then it looks like the most direct way to do that would be using what are called sampling problems, where they don't have a single right answer, right? You're just trying to output samples from some particular probability distribution, like over let's say 50-bit strings, where you could argue that plausibly any classical algorithm would need a much larger amount of time to sample. And so then Google, in 2014, hired this, leader in superconducting qubits named John Martinez. And Martinez said, let's do this. Let's actually, try. It wasn't my proposal because mine and my students called boson sampling was sort of best adapted to optical quantum computing, and they were doing superconducting quantum computing. But they said, let's adapt boson sampling to our setup, and we said, okay, you could do that, and we sort of adapted the theory to what they were building. And then in 2019, they reported a result, which was that using 53 qubits, they could sample from this distribution over 53-bit strings, in a few minutes. And at the time, they estimated that, well, the best classical algorithm that they know would take 10,000 years to do the same thing. And and then that number got picked up by the media, right? And that was kind of unfortunate, right? Because you always have to ask the question, like, do we really know what the best classical algorithm is? Right. And so, since then, starting with IBM, but people have gotten better and better at spoofing these experiments classically. And I would say that the situation right now is that some quantum advantage remains in these experiments. If you measure it, let's say by, how much money does it take to run the machine, or how much electricity does it take? The quantum computer needs a dilution refrigerator that's cooling your chip to 100th of a degree above absolute zero, right? That's a decent amount of electricity right there. Okay, but to simulate it, you need a quite large cluster of classical computers, right? And maybe that's 100 times more electricity or something like that, right? So I think there's some quantum advantage that remains, but it's only by 2 or 3 orders of magnitude. Almost certainly, better quantum supremacy experiments could be done right now that would reestablish a larger gap. But but now what's happened is that the big players like Google, IBM, like they barely even care about quantum supremacy anymore. They just say, let's go straight for error correction. Right. I would actually like to see some, better quantum supremacy experiments now.
Okay, well, let's see if what happens.
Yeah.
Look, before, okay, I was gonna talk about you wrote some beautiful work on, well, I mean, that I found interesting on what it needs to what how much structure is needed for quantum speedups. But I think I want to proceed. We're gonna go the 3 hours, just so you know.
All right.
And I want to spend the last hour of this on the harder questions because we spend less time on them because they're harder questions. But before we leave it, in the last few minutes,
all right,
there's a quote from you that I found interesting. Oh, there's lots of quotes. I should say, I have 20 pages of notes, of which we'll probably go through 4 or 5. But here's a quote from you that I don't understand. Well, maybe.
All right.
If quantum mechanics seems to predict that you can harness an exponential number of amplitudes for computation, then so much the worse for our present understanding of quantum mechanics. I don't understand what
Well,
you meant by
I think
that.
I was no. I was stating that as a possible position that someone could take. I was not myself endorsing that
okay.
position.
Okay. Good. Okay. Maybe I read it wrong. Because there are people who somehow think that quantum mechanics is wrong. I don't know what. Well, I do. One of them is my good friend Gerhard Toof, too.
Right. That's right. He does believe that, but he also, he has a particular idea for a classical theory that would replace quantum mechanics. But, I would say that it can't even explain the violation of the Bell inequality without postulating like what to my mind is like a giant cosmic conspiracy theory.
Yeah, I agree. But he has a good track record. So I'm going to, he's earned the right to, like I say about Bob Dylan, he's earned the right to do whatever he wants. And so it's Gerhard who solved most of the problems of the physics in the 1970s. Many of them, he can do whatever the heck he wants, and he's worth listening to. There's some people I would chalk off. But anyway, so we will see, of course. That's the great thing. Coming back to
that's right. Like either way, let's find out the truth. It's like
quantum mechanics.
I like the skeptics of quantum computing. I believe that they're probably wrong. But if they were right, then that would be even more exciting.
Yeah, it would be even more exciting. Exactly.
Yeah, that's right.
And coming back to Feynman, it's really his interest was learning about quantum mechanics, and we may.
That's right.
I would argue we'll get to whether it's relevant. You talk about the philosophers. You wrote a whole 50-page article which I had to plow through. Where you're talking to philosophers about questions that I may be of interest to philosophers, but not to physicists, as far as I'm concerned.
All right.
But we'll get there because we're going to be led there in the next half hour. I want to talk about computational complexity, which is really your I don't know why the forte, but I think it's what your real, from what I can tell, your real heart is an understanding, which is different than, so complexity is different than computability. Now, obviously, we don't have time to do justice to this, nor could I think, do justice, as much as I've tried to wrap my head around it. But there are a few things I think we can talk about. One is that why don't you talk about the difference between complexity and computability?
So computability is the field that you could say Alan Turing, and his friends started in the 1930s when they created computer science in the first place, right? It said that computer science is one of the only fields that was born with the knowledge of its own limitations, right? And so in the very same paper,
Okay.
just one of the most famous papers of the 20th century, where Alan Turing introduced the Turing machine, right, which is the mathematical model for what we would now call a programmable computer. He also proved a theorem that said that there are some well-defined problems that a Turing machine cannot solve. Okay, regardless of how much time or memory you might give it. Okay, and the famous example there is called the halting problem, right? And it's a problem where you are given as input a Turing machine, or in other words, a description of a computer program. It could be in any programming language of your choice, and you need to decide whether that program will ever stop running or not. Okay. So, now like at first glance, that problem might not seem so hard, right? Like if you think about, anyone with experience programming would say, yeah, I can just kind of stare at the program. I can see, does it have an infinite loop? Does it not have one? Okay. But, you can easily invent, incredibly hard examples. So for example, imagine a program that just checks all of the even numbers, 4 and higher, okay, and tries to write each one as a sum of 2 prime numbers, okay, and it halts only if it finds an even number that cannot be written as a sum of 2 primes, right? Then this is a program that halts if and only if it finds a counterexample to the Goldbach conjecture, saying every even number 4 and above is a sum of 2 primes. That is still an unsolved problem in number theory, right? And so solving the halting problem, would automatically also solve, a large fraction of the great unsolved problems in math, right? Which can be phrased as, does some computer program ever stop running or not? Right. And what Turing said is that, yes, there are specific programs where we can figure out whether they halt or not, but there cannot be any general method, at least using computer programs themselves for solving this halting problem. And the way he did that was a self-referential argument, which is, I think, justly famous. I mean, he was inspired by Gödel's incompleteness theorem, which had been proved just a few years earlier, and and even before that by Cantor's discovery, of the different orders of infinity. Okay, but what Turing basically said was that suppose to the contrary, that you had a program that could solve the halting problem. So it took any program and determine whether it halts or not. Then you could modify this program, to basically be one that would take itself as input, take its own code as input, okay, and do the opposite of whatever it does. Okay, so it could analyze itself, and if it determines that it is going to halt, then it would run forever. And if it determines that it would run forever, then it would halt. Okay, and that's a contradiction.
Yeah.
And the only conclusion is that the program can't have existed in the first place. So, computability theory, in the decades since the 1930s was developed to, a very high level of sophistication. People discovered that, there are other interesting examples of uncomputable problems. So for example, if I just give you an equation, and I ask you, does it have a whole number solution? So solving a Diophantine equation, that is equivalent to the halting problem, right?
Oh, okay.
There can be no general algorithm to solve that problem. And again, it's not even a question of time or memory, right? They're just,
It's a mathematical proof.
right. It's a question of finite versus infinite, right? It just, that there is no way to take, the infinite number of possible solutions and rule all of them out in a finite amount of
So
time.
in fact, let's stop for a second. In a
Mhm.
sense, Computability is the question of finite versus infinite, whereas
Yes,
complexity is a finer distinction. Is that, you think, a fair way of saying
exactly,
it?
exactly, exactly. Now, when people started building actual computers, in the 50s and 60s, right? Like some of the first things they wanted to do is, okay, there are all these problems that we know to be computable, so let's try to solve them, right?
Mhm.
Some of them were for example, there was a famous theorem of Tarski that said that for well, deciding whether equations have whole number solutions is uncomputable. If I just want to decide the truth or falsehood of sentences involving real numbers, then
Mhm.
then that problem has an algorithm. Okay, that is computable, right? And so they tried to do that with the mainframe computers of the 50s and 60s.
Mhm.
But then they quickly realized the problem, which is that while Tarski's algorithm, had given an algorithm, the amount of time needed by the algorithm could only be expressed using like a stack of exponentials. It
Mhm.
was like 2 to the 2 to the 2, right? And so, this is not just a practical issue of like, does your program take 10 seconds or 20 seconds, right?
Mhm.
This is a question of, can you do it like within the lifetime of the universe,
Mhm.
right? And so by the 60s, it had become clear to people that we needed to make a finer distinction, among the problems that are computable, which is, an enormous number of problems that we care about.
Mhm.
But we actually need to know further which of those problems have an algorithm with a reasonable scaling.
Mhm.
Okay. And it took a while for people to sort of, converge on sort of what is even the right question to ask there, right? But I would say by the late 60s, it was clear to people that a really crucial distinction was between the problems that require exponential scaling and the problems that allow for polynomial scaling. Okay, so polynomial scaling would mean I use a number of steps that grows only like the size of my input raised to some fixed power, such as 2 or 3, for example.
Mhm.
And now, if I have an algorithm that takes n to the 10,000 time,
Mhm.
n being the size of the input,
Yeah.
okay, then technically that would also be polynomial.
Yeah.
Even though no one would ever pretend that that was
Yeah.
fast in practice,
Yeah.
right? But then on the other side of this chasm are the problems that inherently require an amount of time that grows exponentially with n, right? Such as 2 to the n, for example, or it could be even worse, n factorial, right?
Mhm.
Now, it's complicated. There are, you can be intermediate, between these two. Okay, like n to the log n power would be
Yeah.
would be an example, right? You can have mild exponentials, and you can have as I said, you can have brutal polynomials.
Mhm.
Okay, but empirically, what people found was that the problems that we care about, in practice, tend to organize themselves into,
One or the
first
other.
the polynomial ones that, usually have a pretty mild scaling, such as quadratic, or cubic at worst.
Mhm.
And even if the first algorithm that's discovered is like n to the 10, usually if you put enough effort into it, you can make that n to the 5, and then you can make it n to the 4, right? You can whittle down the exponent from
Mhm.
one year to the next. And so people got really, really good at that game. Okay, and then on the other side, there are the problems with exponential scaling, okay, that have a sort of inherent intractability to them, right? And that's, not just a contingent statement about, this year's model of computers, right?
Mhm.
That seems like something inherent, right? And now, it could have been a priori that there would just be, thousands of different hard problems, that would have exponential scaling for thousands of different reasons. Okay. But
Yeah.
now we get to, the key discovery in the 1970s, which is that, of the problems that have exponential scaling, almost always it's just for one of the same few reasons. right? And this was this key discovery, which was called NP-completeness.
Okay, yeah. So what? So
Yeah,
now, good. I wanted to get, I want. Let's talk about P and NP.
sure.
Which, by the way, I actually, yeah. Anyway, let's talk about P and NP, which I think I only
Yeah.
fully understood reading you as well.
All right, sure. So P, well, stands for polynomial time, and it's just the class of all of the problems that have an algorithm, on a conventional computer
Yeah.
that solves, any instance of that problem,
Hmm.
with polynomial scaling. Okay,
Yeah.
so you can think of it, loosely as the class of all of the efficiently solvable problems.
Yeah.
Okay, so examples of problems in P would be I give you a map and I ask you, is every city reachable from by every other city, right? Like I
Hmm.
give you a graph, are all the vertices connected to each other? Okay. Less obvious examples. I give you an integer, say written in binary. I
Hmm.
ask you, is it prime or composite? Okay. It turns out that if you just want to know whether a number is prime, that can be done way, way more efficiently on a classical computer than we know how to actually find the factors if
Okay.
it's
Oh,
composite,
okay.
right? So that's a
Mm.
non-obvious fact. Okay,
Yeah.
but primality testing was discovered in 2002 to be in P. Um, Linear programming.
Right.
So like I give you a system of linear constraints and I ask, is there a point that satisfies all of those constraints? Right. Or even simpler than
Mm.
that, solving, I give you a set of linear equations. I ask, does it, is there a solution? Like, is this matrix invertible or not? I give you a list of boys and girls and which ones are willing to date which other ones. And I ask you, can they all be paired off in a way where everyone is happy? That's called the perfect matching problem. Okay.
And these kind of
So,
problems, I mean, I couldn't resist this quote that you gave from
hmm,
Turing, what you just said. It's not obvious that, I mean, it's certainly not obvious someone that knowing whether something's prime or not is going to be a lot easier than finding its factors. But he said,
yep.
the view that machines cannot give rise to surprises is due, I believe, to a fallacy to which philosophers and mathematicians are particularly subject. It is This is the assumption that as soon as a fact is presented to a mind, all consequences of that fact spring into the mind simultaneously with it. It's a very useful assumption under many circumstances, but one too easily forgets that it is false. And if you ever
Yeah, that's a
tried it, it
great.
is false.
Yeah, it's a great quote. I mean, Turing often had excellent ways of putting things. But so okay, so that was P. That's the class of all the efficiently solvable problems.
Okay.
And when undergraduates, major in computer science, in their algorithms class, they'll learn, many examples of problems that are in P and
Yeah.
why they're in P. Right. Okay, but then there's NP,
Hmm.
which it doesn't stand for not
Yeah,
polynomial.
which is what for a
Stands
long time I always thought that's what it stood
yeah,
for.
yeah, right. Common, issue. I mean, look, we're just not as good at naming things as physicists are, right? You've got names like quark, black hole, right? We're stuck with, P and NP, but all right, but NP stands for non-deterministic polynomial time, and you can think of it as the class of all of the problems where there is a polynomial time algorithm that is an efficient algorithm for checking an answer to see whether it's correct or not, right? Not necessarily for finding the answer,
Yeah,
but just for checking.
we're checking to see if
Okay.
it's right.
So so factoring is an example of an NP problem, right? Like it might, if I give you a huge composite number, it might be incredibly hard to find its prime factors. But once you found them, if someone doesn't believe you, then it's easy to
Multiply them.
convince them. You just show them the factors,
Yeah.
and with their computer, they can easily multiply them together and check that they work, and they can even check that they're prime, right? So,
Mhm.
so we would say that factoring is an NP problem. Okay, but there are many other examples, like so the famous traveling salesman problem
Mhm.
says, I tell you the distance between each pair of cities, and now I ask, is there a route that visits every city with at most 5,000 miles total or something
Mhm.
like that, right? And this might require some, enormous combinatorial search to find that path. But if you succeed at finding it, then it's very easy to check. You just add up the distances,
Yeah.
right? And a huge number of games and puzzles have the same character. So Sudoku, right? Many people have experience that it can take a while to solve, but it's easy to check. Jigsaw puzzles, okay, have the same character. And in fact, now we get a little bit meta, but math itself has the same character, right? If I ask you, give me a proof of this theorem, right? Like, since the work of Bertrand Russell and his friends a century ago, we have known completely formal languages for expressing mathematics, right? Where even a computer can check the validity of a proof, right? But that still doesn't mean that the computer has a way to find the proof in any reasonable amount of time, right? So if I ask, like, is there, I give you a theorem, like, or a conjecture, like the Riemann hypothesis or something, and I ask, is there a proof of it in this formal language that is at most, a billion symbols long, right? That's another example of an NP problem. Okay. And so now we can already pose, the central unsolved problem
The biggest
of
problem, the clay problem.
theoretical computer science for the last half century, which is, does P equal NP? Okay, so is there a polynomial time algorithm to solve all of the NP problems? That is, all of the problems where you can efficiently check a solution.
So we know one is a subset of the other.
That's right. P is contained in NP. So, if you can solve a problem yourself, then clearly you can also verify the solution, right? Like, but the question is, if you can verify a solution efficiently, then does that also mean that you can find a solution efficiently, right? And I like to joke that, like, if we had been physicists rather than mathematicians, we would have just said, of course not. Next question. Right? We would have declared that P is not equal to NP as a law of nature, and maybe given ourselves Nobel Prizes for its discovery. And if later it turned out that P equals NP, well, then that could just be more Nobel Prizes, right?
Okay. I wouldn't quite go so far, but in any case,
No, okay.
we might do. And by the way, and this will come to the next half hour. What we might do as a physicist is say, I have other problems I can solve. I'm not going to worry about that one.
Yeah, no, of course. So, you can choose, and I mean, especially given the experience of the last half century, anyone could be forgiven for not choosing to spend their time on the P versus NP problem.
But it's got profound implications.
Yes.
And I want to I want to lead them in directions, really the directions of what can computers do?
Yes.
And B, can they think? Ultimately, in my mind.
Yeah, sure, absolutely. No, but just to tie things up, I wanted to say, the key discovery that people made in the early 70s was that a huge number of problems that you might care about, including the traveling salesman problem, including actually Sudoku puzzles, it turns out, including finding a bunch of people in a social network who are all friends with each other, minimizing the energy of, like, of a folded protein. So practical problems also, right? A huge number of these problems actually, you can prove that they are solvable in polynomial time if and only if P equals NP. Okay, so each of these problems in itself individually encodes the entire difficulty of the P versus NP problem. Okay, that was the non-obvious part. Okay, and problems that have this property, that they're sort of NP problems that are at least as hard as any other problem in NP, these are what are called the NP-complete problems. Okay, and so what was discovered is that, like, if you come up with some problem that involves, like, satisfying a whole bunch of different constraints, that might conflict with each other, and you have some combinatorial explosion of
Hmm.
of ways to set your variables. Like such problems will generally will be NP complete unless they have a very good reason not to be. Okay.
Okay, now,
Now, a factoring is an exception. Okay. Factoring is an NP problem that seems to not be NP complete.
so
It
there,
has
it's nice to
very
know there
special
are some
structure. Right.
non-incomplete
There
complete
are right.
problems.
There are outliers. Factoring seems to be like in a no man's land between P and NP complete.
But
Right.
okay, now you
Yeah.
gave some examples. So this sounds a little
Yes.
abstract for most people, but
Okay.
let's bring it down to earth in a way,
Sure.
in another
Yeah.
way,
Yeah.
which
Sure.
is the reasons to think that P doesn't equal NP are
Hmm.
many
Yeah.
as a physicist, let's say.
Hmm.
And one of the reasons is the analogy that I like. So this is the idea of NP are problems that you can show, you can verify the solution, you can verify it's good in a finite
Hmm.
time or a
Hmm.
polynomial time, even if you can't solve
Hmm.
it. But
Hmm.
if that's equivalent to the problems that could be solved in a polynomial time, then the analogy you use, well, there are a bunch of them, but one would be, so if anyone is able to appreciate a great symphony, they could also compose one themselves. So
Yeah.
knowing it's great is the NP part. I can
Right.
verify that it's great, but if it's
Yeah.
equal to P, then I must be able to do it. And for
Right.
those
Like
of us who haven't been able to
our
compose a great
intuition would.
symphony,
Right. I mean, most people's intuition would be like, as soon as they understand the question, they'd be like, of course these are different, right? Of
yeah.
course you might need X. Or, now the tricky part is that there are problems. Like, to go back to that example from before, like I give you a bunch of boys and girls. I tell
Hmm.
you who's willing to date whom, right?
Hmm.
You have to pair them off so that everyone is with a partner that they like.
Hmm.
That problem also seems on its face like it would require an exponential search,
Hmm.
right? Like maybe that one is NP complete, but then it's not. There's a clever algorithm for it that lets you avoid the, considering exponentially many solutions.
Well, in
Right?
fact,
And so,
it
yeah.
it's really important. I want to go back. I want to say that a lot of times
Hmm.
things just look so hard you give up. But smart
Hmm.
people, and one of them, which I think is really important, was the misunderstanding. You mention it in one of your articles,
Mm.
which is evolution.
Yeah.
That one of the mistakes that people make who look for intelligent design, and I forget which of the great
Mhm.
scientists made that mistake himself. I don't know if it's Turing, but
No, no, no. So Gödel had a quote. I mean,
Gödel,
it's
yeah,
not that
Gödel.
it's not that he didn't understand natural selection. He just thought he dreamed of proving a theorem that would say that it was vanishingly unlikely to have, produced, intelligent life in a mere 4 billion
Yeah, I
years.
mean, and that's, by
And
the
so,
way, still that's still
he
the
was he
obstacle.
was he was kind of a mystic. Now, I would not put very good odds on being able to prove that theorem because,
Well, yeah,
I think
exactly. I
that
mean, I think we're a countertemp. But by the way, it's really
yeah,
important because there's still I
yeah,
every day when I debate these people say, look how complex even a DNA molecules.
yeah,
You can't
yeah.
do that, and so
Mhm.
you can't make the assumption just because something's complicated that it's impossibly
Right.
complicated.
That's right. No, I mean, Dawkins, calls this the argument from personal incredulity, right?
Yeah, yeah.
Just because you can't see an efficient way for something to be found doesn't mean that there isn't one. And that was a lesson that computer scientists, had to have seared into their consciousness from, very early on, right? And that's why the P versus NP problem is so difficult, right? Because how do you rule out that there's some clever approach that just everyone has missed for half a
Well, okay,
century?
so I
Yeah,
want to focus because again, there's so
yeah.
much we could talk about because of
Yeah,
lack of
yeah,
time. I want to focus on this idea of thinking. I want to focus on a Turing test. In principle, a
okay.
Turing test is kind of an NP kind of problem, right? Can I recognize that I might not be able to do it, but can I
Mhm.
recognize that a computer is a computer or a thinking human being? And
Well, okay. I mean, I would say, what Turing was trying to do in this famous paper in 1950 was to give an operational criterion, right? By which, we could decide whether to call something intelligent or not, right? Now, technically, he wasn't saying that it's an NP problem because, after all, he wasn't reducing it to a computational problem. He still needed a human judge,
yeah,
right?
yeah, yeah.
And
But I want to get
Turing might
back to
have
that.
believed, I mean, Turing, like many people today, might well have believed that there is nothing that the human brain is doing, that can't be simulated by a computer, right? But in formulating the Turing test, he still had the judge be a human being.
Yeah, no, and
Yeah.
I'm
Yeah,
doing
yeah.
this with malice of forethought because I want to lead
Yeah,
to
yeah,
AI
okay,
safety,
fine.
which I
Fine,
think which
fine.
is related to this. I
Yes.
mean,
Okay.
AI sentience. So let
Yeah,
me
yeah, yeah.
ask you a question. Um, if P does not equal NP,
Yes.
does that imply that there's no effective Turing test that's possible? That there's no way to tell ultimately people for a long time, if you're interested in seeing if ChatGPT is intelligent,
Mhm.
if P is not equal to NP, there's no effective way that you can do it ultimately. So you
I
really
don't I
don't
don't
know if it's intelligent.
I don't think it does, to be honest. I mean, I think that, the question, the technical question of P versus NP, and the, informal question of how do we recognize intelligence, right? They do interact with each other in some ways, right? But they're not the same question.
Yeah.
They cut across each other in a
Well,
kind of
the
interesting
reason I'm
way.
asking is
And
one of the
yeah,
things
yeah,
that upsets me about a lot of this
yeah.
AI safety stuff to begin with, and singularity stuff,
Mhm.
is how little time is spent on actually talking about what human intelligence is or sentience. And since
No.
we don't really understand that at all, we don't understand a consciousness. I wrote a book in the whole last chapter is
Mhm.
about how little we understand consciousness. So if we
Sure.
don't understand human consciousness, how can we
Well,
be so
I
concerned
mean,
about anyway?
I would say all of that is completely true. Now, what, the people worried about AI existential risk, what they would say is that our lack of understanding is not a reason to be calm, right?
Yeah, okay, yeah.
And they would say that, the unbelievable success, in just, scaled up machine learning, that we've witnessed over the past few years, demonstrates that we don't have to deeply understand some, facet of intelligence in order to be able to replicate it.
In order to be able to replicate, but then the question
Yeah,
is it replicating it and
yeah.
being the same, or of course the
Of
million dollar
course, of
question,
course. But
literally.
if you were, so let's say, there's a philosophical question
Yes.
of, like, is the AI truly conscious? Is there
Yeah.
anything that it's like to be the AI? How could we ever know that? But then there's also the practical question: what effects is this AI going to have on civilization?
Yeah,
Right?
and we'll get there. Yeah, we'll get
And
there in just a
what the
moment.
AI what the AI risk people would say is that we don't have to answer the first question
Yeah, of course. But I
in
want to
order
deal
to
with the
have
first
worries
question
about the
before
second
we get
question,
to the second
right?
question in the last half hour, which is
Yeah, right.
okay.
And no, but you could say that also what Turing was trying to do with the Turing test was also to pull apart those two questions in some sense. He
Yeah,
was
yeah.
saying, let's set aside the question of is the machine conscious, and let's just focus on this empirical question of can you build a machine that acts in a way that we cannot tell apart from a human?
Yeah,
Yeah.
and I guess that's what that's why I asked is MP
Mm,
equal not
mm,
equal to and not equal to NP
yeah.
because I can
Yeah.
imagine that there's no polynomial way, there's no finite time way in which you could do an algorithm by which you could distinguish whether the computer has solved what it means by
Mhm.
being intelligent. That's what I
Right.
mean by it. I mean, I could imagine P not equal to NP would be a statement that it's plausible, it's
Mhm.
possible that there is just simply no way to ultimately do the Turing test. That's why I asked you the question.
Well, okay, but I mean, now that I'm spending a couple of years, moonlighting in AI, or,
Mhm.
working with
Yeah.
OpenAI, I am forced to get comfortable with the fact that in AI you usually don't have formal definitions of
Yeah.
the concepts that you want, and and you have to deal with them anyway, because they are changing the world,
Because
right?
they're changing the
And
world.
so,
That's right.
you could say, even, without, having a mathematical definition of when is a machine intelligent and when is it not, right? You have to answer questions like, how intelligent do we expect GPT-5 to be, and we can try to operationalize that in various ways. Like, will it be able to get a gold medal on the International Math Olympiad, right? And
Yeah, yeah.
and none of those questions will capture all the facets of what we care about, but
Yeah.
at least they give us some empirical handle on it.
Okay, let me
Now P versus NP is a technical question, right? That, it's a profound one, but it's one that, I think, it's sort of, it's neither necessary nor sufficient for, for having human level AI, right?
Yeah,
Because
yeah,
like you could
okay.
say, even in a world where P is not equal to NP, okay, that would mean that no computer program could, sort of magically guess the answers to, any well-posed mathematical question, whose answer is can be efficiently checked. But that wouldn't say anything about the impossibility of AI, because after all, we can't do that either,
Yeah, yeah, exactly.
right?
No, and my
Right?
point is ultimately it may just be a question of semantics to distinguish.
Yeah. Yeah. No. No. And
But let me
I mean,
ask you one last
yeah. Go
question
on.
before we hit the
Sure.
heart of this,
All right. Fine.
which is, well, this isn't, maybe it's irrelevant. If it's irrelevant, we'll just do it in a minute, but
All
it
right.
intrigued me.
Sure.
So you might say there are limits to, so human intelligence as a classical computer, or whatever you want to call it, can do certain
Hmm.
things, but it's limited and can't do things that, solve certain questions in polynomial time. But here's my question.
Yeah.
If humans can build quantum computers,
Hmm.
and quantum computers can solve it in polynomial times, then haven't essentially human intelligence solved the problem in polynomial time? Or is that just a
Yeah. So, okay. You could say that, we are using, maybe the way a computer scientist would say is that we are then using the physical world as an oracle, uh, to do something that our unaided brains could not. I mean,
but
then
we do that
again,
all the time?
of course, we already use classical computers in that way
Where
as
we use
oracles,
telescopes, we
but
use every
right.
bit of scientific equipment.
Quantum computing, of course, also feeds into the discussion of P and NP. So,
Okay.
there is what my former advisor, Umesh Vazirani, what he did 30 years ago is to define the quantum generalization of the class P. Okay, so the class of all the problems that a quantum computer could solve in polynomial time, and that class we call BQP, bounded error quantum polynomial time,
Mm-hmm.
right? And now you have a new set of questions to ask. One of them is P equal to BQP, right? And
Mm-hmm.
Shor's algorithm, then, which came a year later, gave some evidence that the answer is no. It said if, P can only be equal to BQP if factoring numbers is in P, right?
Mm-hmm.
Because, factoring, Shor says,
Yeah.
is a BQP problem. Okay, but then we could also ask the question, what is the relationship between NP and BQP, right? And we still don't know. We don't know that either of them is contained in the other. Okay, so they could
True.
just be incomparable. Okay, but when you ask, is NP in BQP, that's just another way of asking, could quantum computers solve NP-complete problems in polynomial time? And so we, of course, we don't know, because we don't even know if classical computers can
Yeah.
do it. So how could we know, prove that quantum computers can't? But it's generally believed today that the answer is no. Okay, that for NP-complete problems, quantum computers, they can get that square root speed up from Grover's algorithm,
Uh-huh.
but probably not more than that, right? And that does
Okay.
not reduce exponential to polynomial.
Okay, for those who've borne with us for this long, let's let where we. I mean, I hope. I think they're fascinating questions, but the question that now is in the minds of
Yes.
everybody
All
is
right.
Terminator, our future, and
Yeah.
you uh, had decided, and I was going to spend more time into, and you've
Mhm.
written about how you got seduced into going into this. You've taken at least 1 year off and working for
Yeah.
OpenAI.
It's now a second year also.
Oh, you
So
did? Okay. When I last read
yeah,
this, okay. So they seduced you.
it will be 2 years, and after that, I'll have to decide how to spend the rest of
Yeah.
my life,
Yeah.
to go back
Okay.
to quantum
But you have been
computing, or
you've
yeah.
been drawn onto the dark side. And
I don't know if it's look,
it could
I'm
be.
working on the safety team.
Yeah, I know it's the light side. I'm joking. Um, and anyway, this question of that, I signed a petition about ChatGPT because, and by the way,
Which petition?
I should tell you where I'm coming from. I'm nowhere. Kind of like you. I'm not even a reformed alignment person. I'm kind of a agnostic alignment person in the
All
sense
right.
that I'm not as worried as many people are. I'm more interested in what AI can do than being worried about it destroying humanity. But
Mhm.
there's no doubt that there are these questions, and
Okay.
and uh, and so you're right that one needs to look, and the reason I signed that ChatGPT thing was not because I was worried about it taking over the
So
world, but I was worried it was
which
being
thing
trained to
did
be
you
too
sign?
woke.
Was it the 6 month? Was it the call for the 6 month
Yeah, yeah,
pause?
yeah. It's a call for
Okay,
6 months. I
that
agree
one. Yeah.
because at the time I even wrote an article about how woke it was, and I was a little upset about that. It wasn't being
No, no, no.
trained right.
The main people advocating for this, they're I can assure you that the woke people hate them and vice versa.
Yeah, yeah,
So
yeah, yeah. Anyway, yeah, no, no, exactly. But you also point
yes.
out, well, actually, kind of interestingly, you say there's two aspects to AI safety. There's the AI ethics groups, and there's the AI
Yes.
alignment groups, and you point out that they hate each other, which I
Yes,
think is,
that's right.
and it does, and you use the example that I use in many other cases, which is the People's Front for Judea, which is the Judea's People's Front from
Yes.
Monty
Yeah,
Python's
exactly.
Life of Brian. But
Exactly.
why don't in the 20 minutes we have left or so,
Yes.
why don't you describe briefly AI alignment versus ethics? And then I want to
Sure.
talk about alignment and ChatGPT a little bit. And then I
Sure.
do want to talk about the two things you've been working on, which I find fascinating, which is sort of
All right.
watermarking and backdoor
All
kind of
right.
ways
All
to
right.
control things.
All right. Sure. So I would say that AI ethics is the field where people are mostly worried about, current or very near term AIs being used to generate misinformation, to entrench the power of some groups over other groups, to output biased answers to be used for political propaganda campaigns, things like that. Um, and then AI alignment is the field where people are worried about, how do you get a really powerful AI to be aligned with our values. So, if you imagine that AI, at some point just becomes able to do pretty much everything that we can do, better than we do
Yeah.
it, right?
Uh-huh.
Then you imagine that at some point it is basically to us as we are to orangutans,
Hmm.
right? And then, well, how well do we treat orangutans, right? Well,
Yeah.
they mostly just survive in a few zoos and jungles at our pleasure, right?
Yeah.
So how do you get a super intelligence, to prioritize human welfare, or to value humanity at all? Okay, and so the ethics people are mostly concerned about some people using AI as a tool to get power over other
Or it
people,
becoming
right?
racist or
Whereas
not racist
whereas
or
whereas the
whatever.
alignment people are mostly concerned about, like, all of humanity is in this together against the
Okay, so let
a future AI.
and they're both real worries. Let me not minimize
Yeah,
one,
that's
but
right.
I
That's
think
right. I
the
don't regard either as absurd things to worry about at all. And I sort of wish that we were able to have a scientific field of AI safety that could address the full range of things that you
but
might be worried about.
it's not a but the point is it's not really a fully scientific question, which is
Hmm.
interesting, which is the reason you stayed away from it. And um
Well,
and
I
and
mean, I usually, like, was able to do the best with questions that I could formulate mathematically, right?
well, I mean
And
that's the way it is in
you
physics.
know,
You know
yeah,
you know
that was
you got to my PhD supervisor once told me don't think, work. But but
yeah.
but the
Well,
point is
right,
that
right.
in physics, graduate students and students want to solve these big problems, but but first you have to solve the small problems, and the best thing to
That's
do is
right.
solve a problem that's actually solvable, or at least
Yes.
which you can formulate and you know what the
Yeah.
problem is, which is
Yeah.
itself
No.
a
No.
major.
No.
And so your
Absolutely.
point was, which I
Absolutely.
think is interesting, is that for a long time these things were quite theoretical. And I have to say, I attended a bunch of
Well,
the early meetings. Were you at a
hmm,
Silomar? I can't. Maybe we met. We
nah.
saw. Anyway, I went to a Silomar, and I heard these meetings about AI and all the worries that the philosophers had, and it was a lot of talk. And I just sort of
Yeah.
felt it was just talk. But
Yeah. Well.
Chat GPT and the new things you've pointed out to you that I'm sorry I'm leading you through it, but I want to get to it
No, it's
before you.
fine. It's
I
fine.
believe is hey, here's a empirical example, and now we can
Yes.
ask empirical questions and maybe
Yes.
make empirical progress instead of just
Yes.
talking.
Yeah.
Is
Yeah.
that fair?
Yeah, that is very fair. I mean, no, as soon as I saw GPT-3, which was, during the pandemic, right?
Hmm.
It was, I think at the time there were people saying, oh, this is just another chatbot. This is
Yeah.
like Eliza from the 1960s.
Yeah.
But, I knew, I had tried Eliza and I
Yeah.
tried this, and it's
Yeah.
clear that this is a phase change in, the capabilities that humans have. I think the only, technological thing in my lifetime that produced, a similar feeling in me was, when I first saw the internet, as a, or the web as a 12 or
Uh-huh.
13-year-old.
Well, exactly. I mean, it
Yeah.
it is, but it is and it isn't. I mean,
Yeah.
well,
Mm.
let's get around. If we don't get to it, you and I both agree, and as does everyone but one person, that ChatGPT is not thinking, and it's not sentient.
Wait. I mean, no, that it all depends what you mean by thinking. I mean,
Well, it's not. It's
I don't personally regard it as conscious or as
conscious.
sentient,
Yeah, yeah.
right?
Okay, it's not.
Although even that, I don't think it's as obvious as many people make it out to be. But
Okay.
I don't personally regard it as sentient, right? But thinking, well, that all depends. What do you mean by thinking?
Okay, I meant sentient. I didn't mean thinking.
Okay,
Okay, I used the wrong word. But let me step back a bit, because
yeah.
one of the things that I still don't understand about this alignment thing, I
Mm,
remember I remember two well-known philosophers get up on stage and say we have to, like make Asimov's rules. We have to
mm.
make sure that computers are aligned with human values. And
Yes.
both me and Jeffrey Sachs got up at the same time. The economist Jeffrey Sachs, I don't know
Yeah.
if you know him,
Yeah.
said,
Oh
"What do you
yeah.
mean by human values? I
Right.
don't know what
No,
human values
of
are. So
course,
what the
of
hell?
course.
If you want to look at human values by seeing what's
Right,
happening in the world, you won't find any
right,
human values.
right.
So what are we talking about when we talk about
Of,
alignment?"
of course, there's the question of whose values,
Yeah.
and that's not lost on anyone who has seriously thought about this,
Well,
right?
some
Uh,
people who were pretty
but
serious would
yeah.
have thought
But
about it.
we can just crunch. We can put this in very practical terms, right? Like, what should, a company like OpenAI be doing? They don't want to unleash something that's going to, be horrible for the world, right?
I guess the
But
point is that the only human value we
you
can
can now ask, there are immediate, already now sort of moral questions. Like, some people think, there's a moral obligation to open source,
yeah.
these models, like give anyone access to them, let them tinker with them so that they're not in the control of a few companies. Other people think that that's utterly insane. It's like that it would be like open sourcing thermonuclear weapons, right?
Yeah,
And
exactly.
no, like, we have to keep these things under very tight control, right? So, they're like, you may not be able to scientifically answer a moral question, and yet it still doesn't relieve you from having to answer
Yeah,
it.
exactly.
Yeah,
You said there's a
yeah.
lot. Life isn't scientific. If it was, we'd all be scientists, and the world would be an easier place to deal with.
Yeah,
But
yeah.
but we
I mean,
could
yeah,
say,
you do hope that science can inform these questions, of
yeah,
course,
yeah,
and
you do hope so, and
that's where AI safety comes in.
yeah,
Yes.
yeah, you
Yeah,
do
yeah,
hope that, and I get become more
yeah.
pessimistic over time. But
Mm.
but um, one could say though that the only that clearly a universal human value is to preserve humanity so it doesn't end. But if you say that, then it's clear we do things that we built nuclear weapons.
Yeah,
So it's not clearly a universal human value. But
yeah.
but
So,
what
so I
so
mean, one idea that Eliezer Yudkowsky, who was sort of like the prophet of this area, that he
yeah.
likes to talk about, is called coherent extrapolated volition, which
Hmm.
basically means, what you would really like once you have the super intelligent AI is not to tell it, just copy the values that you see humans, enacting, in real life. That would be terrible. What you want to tell the AI is sort of like simulate the humans, having a moral philosophy seminar for 10,000 years, where they would refine their intuitions and get better and better and go through, 10,000 years of the same process that led us, to abolish slavery and to, give women the right to
Yeah.
vote and all these things that we all regard as moral progress, and simulate that process until it reaches some termination point. And then whatever values, your simulation ends up with, then those are the values you should enact. that's that even that idea can be criticized as well, but
Well, of
at
course, you
least
could say they are. You could argue that that moral progress has led to a civilization that ultimately is bad for the planet, and you might say that the ultimate end of that is to say, well, planet's going to be better off if there aren't humans on it. You might argue that's illogical. And I mean, if you're thinking about, say,
right.
in terms of you talk about effective altruism, I know you lectured to. So I just did a podcast with Peter Singer, and might
mm,
say that if you really think that the well-being of all animals is equivalent,
mhm,
and you might
mhm.
say, well, then the human well-being conflicts with that, and
Yeah, I mean, you could also imagine an AI that would reason that, if humans survive and they colonize the galaxy, then they are more likely than not to become a scourge of the galaxy that will, wipe out all the other civilizations, and therefore, the whole, universe will be happier if it kills the humans, right? And so, now, I don't, you know, I think that there is progress that can be made in making it, AIs safer in the more immediate,
yeah, and I want to look at those immediate
without needing to answer these cosmic and
those
bug.
big questions. And in
Yeah,
fact, I
yeah,
mean,
yeah, yeah.
I'm always amazed that people, just as I'm amazed when people see something they don't understand the sky, they decide it's aliens, and I'm going to have to do a debate on
Mm,
that later this month.
yeah.
But also automatically, whenever they think of an quote unquote intelligent AI, they see Terminator.
Mm,
They always see a dystopic future. They never see
mm.
a future in which where human life is in many ways better or could be better.
Oh,
Just as
I
just
mean,
have.
look, I certainly think about the good outcomes, right?
Yeah, I know
I mean,
exactly. I've read you do.
it's even possible. If we think about previous technologies, right? Like some people say, well, the internet has ushered us into a dystopian
Mm.
reality, right? But
But
I don't
but
know.
it's made my life better.
Would I want the internet to have never been invented? I'm not at all sure of that.
No, no.
So like some people said, after 2016, they said, well, look, the original promise of the internet was that it was going to, democratize, speech and give, everyone, the ability to say what they wanted and to influence, the national conversation. And it delivered on that promise. And the only problem is that what a lot of people want is absolutely horrifying,
Yeah, yeah, absolutely. I mean, it's like saying, I mean, when I know, this, there's a lot of information and misinformation,
Yeah.
but you can't deny that, and when I'm out, well, I was just on the tube in London, and,
Yeah.
and I remember me being in Japan 30 years ago where everyone was
Mhm.
staring at games. That's
Mm.
never going to be us. But of course, no one can be on the tube without
Right.
staring at the phone. You might say that's bad, but on the other hand, look at what they can do, and look at
Yeah.
what you can do. So,
Yeah.
it's two sides of the same coin,
Yeah,
but
but I think even the people who are the most doomerist, like they completely agree that they are generally pro technology, right? And they
yeah.
think that AI will make life amazing before it kills us all.
Before it kills us. Now, but
That
let me
tends to,
just, we
at
get
least
near the end.
if we don't get it right,
There's some reasons for
that
hope.
tends to be their position,
There
right?
are reasons for hope, and I want to try and end on an
Yeah,
upbeat note
I
before.
agree. I agree.
One of them you point out, which I think is really important, is that the big concern is that there's a phase transition, that somehow things are moving
Yes.
along, then suddenly, it's like in Terminator. Suddenly, one AI learns how to lie,
Mhm.
and you point out, and this is very important, that
I
the
mean, in some
progress.
sense, our current language models can already lie,
Yeah,
right?
yeah, they can lie,
Yeah,
but
yeah, yeah.
of course they can, and they lie in silly
Mhm,
ways, as you point out, as
mhm,
well as good
mhm,
ways, and you can
mhm.
often trip them up on as a result.
Right,
But
but
they
no,
can
but like
always lie.
you can give them a goal and they can figure out to lie in pursuit of that
Yeah,
goal.
yeah,
Yeah,
exactly.
yeah,
But
yeah,
here's the point. But do it in a way where anyway. So
yeah,
here's the
yeah, yeah.
question: is so now but you point out, and this is important, that if you look at empirically,
Mhm,
what's happening is as they learn, as you say, it's like your students. It's not there's a phase range. You see them make the mistakes as they're learning. It's not
mhm.
as if
Yeah.
they surprise you and suddenly having learned integral calculus when before the day before they were learning how to add.
Yeah.
And
Yeah, yeah, no, they do. They are sort of progressing through the curriculum. Like a couple years ago, they were in, elementary school, maybe in terms of their ability to do math problems. Now they're in high school or undergrad. They're still not in grad school, right? But but like you could say that progress has been continuous, but it's also been extremely fast, right? And so well, like one confusing thing about this discussion is that every phase transition, right, is actually continuous if you zoom into it closely enough,
closely.
right? And so something could be technically continuous, and yet on the scale of a human lifetime, it could feel like a phase change.
I think
And
physicists
I
would
feel like
say
that might be the situation that we're
physicists
in
would
right
say that's
now.
not quite true, though. First order phase transitions really are.
Oh,
But anyway,
well, all
but
right,
yeah,
all
anyway, but
right.
okay, so that's a cause for hope. But there's a statement you make. I wish I could spend a half an hour on this instead of 10 minutes. We've talked about one of the reasons for optimism. Another reason for pessimism, which interesting quote from you. I think that for better or worse, we're going to see real harm from AI. We're going to see them used, unfortunately, to help plan terrorist attacks, to do really nasty things. But those things at least will be far short of the destruction of civilization. So there will be some bad. There will be some bad, and that's one of the reasons you got involved. That and the fact that you can empirically do things. Why don't you
Mhm.
talk briefly in 5 minutes about watermarking at the very least?
Sure.
Okay.
Sure. So yeah, in AI safety, like you're constantly asked to prognosticate, like what
Yeah.
is going to happen, 20 or 30 years from now, and I can't do that. Like
No one can.
if
I
I
would
could do
argue.
that, I wouldn't be a professor. I'd be an investor, and
Yeah,
I'd be
yeah,
rich,
yeah.
right?
Even investors do
But
it because they get lucky.
I was happy that, in summer of 2022 that at least I was able to see 3 months ahead.
Yeah.
Okay. So before ChatGPT came out, like I had this moment of terror where I was like, oh my God, like every student is going to be using this to cheat on their homework, aren't
Yeah.
they? Or
Yeah.
at least they're going to be sorely tempted to, right? And I get all of these trolls on my blog, some of whom put incredible energy into
Yeah.
their craft, I guess,
Yeah.
right? But I'm like, wow, this is going to make, attacking every discussion forum on the internet so trivial to do, right?
Mhm.
The Russian government, for example, could spam every comment section with pro-Putin propaganda,
Yeah. Yeah. Yeah.
that seems responsive to whatever came before it, right? And you don't even need a building full of people to do this, right?
Yeah.
You just have GPT do it for you. And so then, for all of the, and you could also have GPT impersonate someone, right? If you have enough examples of someone's writing, you could say, produce more writing in the same style where this person confesses to a crime,
Yeah. Yeah.
right? Or, you could, try to whip up a campaign to get someone fired, right?
Mhm.
So all of these different misuses all involve concealing the fact that an AI was involved, right? And I just thought, if you could only make the outputs of a large language model detectable as such, right, then that would simultaneously address all these different misuses. Okay,
Yeah.
so how do we solve, what's now called the provenance problem, or the attribution
Yeah.
problem,
Yeah.
right? Of what came from a language model and what didn't. And there are different approaches that you could imagine. I mean, one approach, which actually has been tried over the last year, is to treat it as yet another AI problem. So you just train a discriminator
Hmm.
model to say, did this text come from a human or did it come from a language model, right?
Yeah.
And you can get, maybe 90, 95% accuracy with that
Uh-huh.
sort of thing. But there's still too high a risk of false positives,
Hmm.
right? Where like people were having fun, like we're like with some of these discriminator models, where like they would say that passages from the Bible or Shakespeare were probably GPT generated,
Yeah.
right?
Yeah.
And and okay, but if you are if you're discriminator model is falsely accusing students of using GPT to cheat, right? Then
Yeah.
that's a huge problem, right?
Yeah. Yeah.
And we've already seen some of that in the
Hmm.
last year. Okay, now a second approach would be, as long as the models are controlled by just a few entities like OpenAI, Google, Anthropic, then they could just store all of the outputs they generate in
Hmm.
some giant database, and then they could let people make queries against that
Yeah.
database. Is this a match for anything that you have generated? Now it's not obvious how to do that in a way that would appropriately reassure people that their privacy is being
Yeah.
preserved, right? That's the main drawback there. Okay, so then I got interested in a third approach, which is called statistical watermarking. Okay, and this is where you slightly change the way that the language model operates. So you're not going inside the neural net and fiddling with the weights, okay, but you are so how does a language model work, to step back, right? What it's doing, it's this big neural net, called a transformer neural net, but it's constantly taking as input a context, which is, let's say, the previous 1,000 or so words, which could be either, the user's prompt, or it could be the words that it itself has already generated,
Yeah.
right?
Okay.
And it feeds those in, and then what it outputs is a probability distribution over the next word. Okay, or technically the next token, it could be a punctuation mark, numeral, whatever. What happened in normal operation is just that you sample from that distribution, right? So people may have noticed that, like, you can submit the same prompt to GPT over and over and get a different output each time, right? And people like that, right? It's the model is inherently probabilistic. Okay, but now we could imagine doing other things. Okay, already in GPT as it now exists, there's a parameter called the temperature, right? And if you set the temperature to 0, then what you're telling GPT to do is always pick the token with the highest probability, right? So in that way, you're making it deterministic.
Yeah.
Okay. But now with watermarking, you would do yet another thing, which is you would use this probability distribution, okay, but generate the next token in a pseudo-random way, okay, a way that looks random, that looks, to any ordinary user like this is just regular GPT output, but secretly you're using a pseudo-random function to pick the next token, and you're doing it in a way that biases some score, like some sum over all the tokens, over all the pairs or trigrams or whatever of tokens of some score, which if you know the key of the pseudo-random function and you have the text in front of you, then you can calculate that score. And you'll see, given enough words, given enough tokens, that score will just be systematically larger in a watermarked output than it will be in an unwatermarked
And
one.
it's
Okay,
great.
so
And the virtue of that, by the way, is, as you point out, that if you just change a few words, it doesn't change anything because you're looking
that's
for
right. That's
large
right.
numbers of.
So yeah, exactly. So we have an approach that is indistinguished, where it produces output that is, to the end user would just be indistinguishable from normal GPT output. And it produces this watermark where you can be, like with a few thousand words, you could be statistically certain, basically, that this came
It's
from
great.
GPT.
I have to
Even with
say,
a few hundred words, you're pretty confident, and it's robust to local
yeah.
modifications. Okay, now what it's I have to be honest here. Okay, what it's not robust to, the problem that we don't know how to solve is, for example, a student asks GPT to write their term paper, but in French,
Yeah, and
and
then
then
they
they
try.
put it into Google Translate,
Yeah.
right? Or even they ask GPT to write their term paper, but insert a random number of exclamation marks between each word and the next, and then they take them out, right? And
Yeah.
and GPT-4, unfortunately, is smart enough that it can usually follow such instructions, right?
Yeah.
And I think that in order to have something that's robust against all of that, we're going to have to figure out how to watermark at the semantic level, like not
Okay.
which would mean going inside of the neural net and doing something to the weights.
Okay. Well, okay. Yeah. And okay. So look, I just, it's a small insight into some things you're doing, but what's great about it is it's real. It's not talk. And just so people feel, look, there are
Yeah.
people like you who are actually thinking about how to do these things, which is important. Now, I
Mhm.
want to
Yeah.
end with the last question. Um,
Okay.
because this is the one I use a lot when I've written
Yeah,
about
I
this.
was
In
going to
fact,
say that the alignment people would say that watermarking is a band-aid, and like
yeah, I know the world is
a
over.
true super AI will laugh it off like so much tissue paper,
Yeah,
and
absolutely.
they might well be
They
right.
might be right,
Okay,
but it's baby
but
steps. You
the
can.
hope is that at least we can learn something. at
Yeah, and
least
it's
we
baby
can
steps.
get,
You do what you can
yeah,
do. If
exactly,
you don't try
exactly.
anything, then all you're
Yeah,
doing is putting your head in the sand and saying, "Wait for it to
no,
be over." Um,
yeah, no, and I
and
should say, I'm not the only one who's trying to do something. I mean,
okay.
I have lots
Well,
of colleagues at OpenAI who
anyway,
are trying lots of other things. But
this is
yeah,
speaking of the
I'm
A.
excited. I'm excited that AI alignment is now, at least partly an empirical subject.
Yeah, absolutely.
Yeah,
And as am
yeah,
I think when I hear you
yeah,
talk about it.
yeah.
But speaking of the align problem and the doom, there have been a number of times when people have looked at technologies and said this is the end of the world. And
Mm,
one of the earliest ones, which intrigued me when I first learned about this, and this is what I wrote about in my last book at the end, is when in the 8th century or 9th century in BC in Greece, the introduction of the alphabet
mm.
and writing came along.
Yes.
And everyone, Plato and others, argued that it was the end of storytelling. It was the end of
Hmm.
storytelling because people wouldn't remember things anymore and they
Hmm.
wouldn't have face-to-face conversations.
Hmm.
And so it was the end. And of course, most people, especially those of us who write, would say that writing actually has improved storytelling, at least
Hmm.
hasn't
Hmm.
hurt it. It's changed everything, and it changed what means
Yeah,
to be human. It really
yeah,
changed what it means to be human. You spend a lot of your
yeah.
time reading,
Arguably, yes.
but
Yeah.
and AI is going to change what it means to be human, but that's not such a bad thing.
Yeah. I
What's your
think,
comment on that?
the lower bound on, how transformative AI will be is that it will merely be like writing, like the printing press, like the computer itself, right? It will merely be another, transformative technology that, does destroy, the old world, the world as it was before that technology existed, but then there's a new world, and we adapt to it, right? I think, the one thing people are worried about that could be different about AI is, like, with every previous technology, you could point to, okay, but obviously you still need humans for X,
Yeah, yeah,
right? Like, the printing press, it copies all the books, but obviously you still need a human to write the books,
yeah,
right?
yeah, yeah.
With every previous thing you could say, but this is what you still need the humans for. And after AI, if you truly have a human level, AGI, then it's not obvious that there's any answer to that question anymore.
Yeah, yeah. Okay. So
Yeah.
the really last question is: are you optimistic or pessimistic?
Um, I mean, I am. I often tend to be a pessimistic person. I mean, maybe it's just because, I was, one of the first things I learned about, as a child was the Holocaust, and
Mm,
that just sort of set my,
yeah. Hmm.
my mental template for what the world is like. But, it's never obvious to me which things to be pessimistic about,
There's
right?
so many
Like,
of them.
it may not be, AI that gets us in the end. It may be something much more pedestrian. But like on a day-to-day level, I'm often pretty happy, right? I mean,
Well, I want
so
to. I've said this. People
yeah.
have heard me say this before. I want to give you this because it changed my life when I
Hmm.
first met Cormac McCarthy, my
Ah,
friend, the writer, and he was
yeah.
such an upbeat guy. And I'd
Hmm.
read his books, and I feel like The
Hmm.
Road or How Country Old Man and the others.
Hmm.
And I said, How can you be so upbeat? And he looked at me and he
Hmm.
said, Well, I'm a pessimist, but that's no reason to be gloomy. And I think
I
that's
love
my
that.
motto, and
Yeah,
I hope it. Look,
that's
all
a
I
good.
can say is I'm a little more optimistic about the world because there are people like you in it. And thank you
Oh, well,
so much for
thank you so much. That means a lot to me.
it
All
really,
right.
and I'm saying it
All right.
truth in my heart. So it's been a pleasure, and we could
Yeah.
spend a lot more time, and I could learn a lot more, and I hope that people have. And thank you for taking the time. And Scott, I hope to see you in real life somewhere. But you take care and
Yeah.
keep up
Yeah.
the good
Like,
work.
take care, and thank you for having me on your podcast.
Oh,
All right.
it's been my pleasure. I hope you enjoyed today's conversation. This podcast is produced by the Origins Project Foundation, a non-profit organization whose goal is to enrich your perspective of your place in the cosmos by providing access to the people who are driving the future of society in the 21st century and to the ideas that are changing our understanding of ourselves and our world. To learn more, please visit origins project foundation.org.